Hi there, my name is Glenn and welcome to the All About Arduino channel. Today I'm going to look at memory. So not so much the hardware like latches and flip-flops and things like that, but more how the Arduino uses the memory, or more specifically how the C++ compiler uses the memory, and the different types of memory and some general tips and traps, and just have a general deep dive into how memory works. Okay, so let's hop into it, and we'll just start off with a bit of theory, which is important to sort of understand the concepts, and then we'll sort of take a deep dive and actually look at how it works on an actual Arduino. Okay, let's get going. Okay, so today I thought I'd take a look at how memory works, and I don't mean like flip-flops and SR registers and latches and so on. I mean actually how the compiler and the software uses the memory and the different types of the memory. So this is more of a software look at memory rather than the hardware. And I'll focus primarily on AVR memory architecture, and specifically the Uno R3, which has an AT Mega 328p, but I might briefly look at a Mega 2560 as well. So in this video, I'll look at the various types of memory, how the memory is used for different purposes and how it's organized, and also have a bit of a deep dive into the actual memory contents and how the compiler uses the memory. There's a few different types of memory. So there's sort of essentially three levels: cache, secondary and tertiary, and there's persistent and volatile or non-persistent. So persistent memory is basically memory that retains its values when you turn the power off. So for example, EEPROM, the flash, a hard drive, SD card, CD, network, cloud storage database, things like that. And volatile is the opposite. When you turn the power off, you lose its settings. So that's the cache, the actual dynamic memory, or the static, the random access memory. You could have sort of secondary, which is external, such as an I2C RAM module or a memory expansion kit. And you can also have some tertiary ones. That's very much less common, but an example might be AWS's EC2 Instant Store. When you turn the power off your cloud server, the content of that is lost. Another example might be something like Pastebin, where you can set an expiry date, so after 2 weeks the content you put up there just disappears. The main difference between primary, secondary and tertiary is sort of how close the memory is to the CPU. Either it's directly wired in, or it might go through some sort of high-speed interface, such as the I2C RAM module. Generally, those tend to be in the vicinity of the computer, either on the main circuit board or plugged in very close, like through a USB or a plug-in adapter or something like that. And then tertiary is a bit further away. And the main difference is speed. So primary will be the fastest access, secondary is sort of next fastest access, and then tertiary, potentially over a wide area network, is the slowest sort of access. So that's the main difference between those three. So I'm going to focus primarily on the AT Mega 328p, which if you look at your Uno R3 board, that's this chip that I've circled here. Some of them have a little much smaller surface mount version, which is sort of about here somewhere. It's the same chip, just the physical packaging is different. So I'm going to focus on the internals of this. And this guy has three types of memory. It has flash, and that's primarily used for your code, but it's also where initializers go, and we'll look at that later on. And there's 32K of that on this particular model, 328p. There's static RAM, this is the volatile memory. There's 2K, and where you have variables like declaring an integer or whatever, that's where those are stored, and these are meant to be updatable. And there's also some memory mapped registers in this address space, so we'll look at that further. And then there's EEPROM, and that's got about 1K, I think it is, of memory. And that's all inside this chip. So you could put all of that code and whatever onto it, take this chip off, give it a little bit of supporting circuitry, and now you have an embedded system that can be running your code, and you don't really need all this extra stuff. Okay, so the next thing I'm going to briefly look at is the CPU architecture, and there's two main ones that are used
these days. Harvard is the one that the AVR MCUs use. And as most things in IT, the lines get blurred, so it isn't quite as black and white as this anymore. But these are the two basic designs. So in the Harvard architecture, there's separate memory and buses for each memory. So you can see here there's a CPU and there's sort of separate memories, and there's all of these lines interconnecting, which is the different buses. So what that means is that the CPU has 3 buses coming out of it. So that means it can actually access 3 different types of memory at the same time. The other architecture is von Neumann architecture, and that's a common, it's typically characterized by a single memory space. These ones all start at 0 and reuse memory addresses, but von Neumann is typically a 0, a contiguous memory up until an upper limit. And it's typically accessed via a single bus, which means only one thing can be accessed at a time. And as I said, it has a linear address space. So there's no right or wrong architecture. They're just different and they have different attributes. And depending upon what the manufacturer is trying to achieve, they might use one or the other, or use this modified Harvard where they use bits of Harvard and bits of von Neumann to suit their purpose. So there's some Wikipedia links there. You can look at those at your leisure and find out more about these as you wish. So let's have a look at the Uno R4, which is an ARM Cortex MCU, which is sort of von Neumann, but it also uses aspects of Harvard, where there's multiple buses, so it's a bit of a combination, so we refer to that as a modified Harvard. There's also your PC, which just has one large block of memory that's a single contiguous address space, and everything sort of pretty much operates out of the RAM, but people do describe Intel CPUs as modified Harvard as well, or PC architecture as a modified Harvard as well. So again, there's no black and white. Everything's a bit fuzzy in IT as technology advances. So they're just examples for you to consider. So let's look at the ARM Cortex. So as I said, it has a single linear address space that starts at 0 and goes all the way up to, I think that's 4 gigabytes. And then throughout there's a mixture, a sprinkling of different types of memory. So I've color-coded it. So there's RAM, which is the green one here. So that's here starting at 2, whatever that is, 2 zeros, and goes for 32K, which goes to 2, whatever it is, and 8,000. And then there's flash, and there's various types of flash sprinkled through here for different purposes. So it's for code and initializers. And then there's this EEPROM, which is the data flash. So this MCU, the ARM Cortex, doesn't actually have the EEPROM technology. Rather, it uses some flash, and that is this blue one. And so it's actually flash memory, but it's configured to operate as EEPROM and appear as EEPROM in the memory address space and how you interact with it. And then, as I said, so these two are persistent, so the memory persists across power cycling. These are designed for writing, I said often, but you really don't want to be writing to it too much because they do typically have a finite number of write cycles, but you can read it as much as you like. And typically flash can only be written under special circumstances. I'm not sure about the rules for AVR, but there is definitely some rules for I'm not sure about the rules for ARM Cortex, but there are definitely some rules for AVR. And then, of course, there's the RAM, which is for transient data. It goes away when you turn the power off. It's read and write as much as you like. And then there's this memory mapped I/O. And in ARM Cortex, that's here and here. There's 2 blocks. And I'll talk about that on the next slide. Okay, and then as I said, this is a modified Harvard architecture because even though it has a single linear address space, the CPU actually has multiple buses which it can access these different types of memories through. So it also can do multiple IOs simultaneously. So here's the AVR CPU architecture. It's the same diagram as I showed earlier, except this time I've color-coded it. So again, we have EEPROM, there's 1K, and that's accessed over this bus here. There's flash 32K, and that's got its own private bus to the CPU, so it can load program instructions whilst it's accessing this green section, which is the RAM. And then there's a memory mapped I/O, and there's 255 bytes of that on this particular MCU, the ATmega 328P. Bigger MCUs like the Mega 2560, they have more space allocated here. And we can see here that the memory mapped I/O shares the same bus as the EEPROM, so you can't do memory mapped I/O and EEPROM at the same time, but you can access RAM and flash at the same time as doing this. So what's this purple bit? Well, there's a few clues here. There's USART 0, so that's the serial port. So these are the registers that manage interaction with the serial device. And again, as I said, the Mega 2560, it has more of this purple space, and that's simply because it has more of these things. So the Mega 2560 has 4 of these guys, so it needs 4 sets of registers for it. Similarly, there's the SPI, the 2-wire interface, that's basically the I2C. There's all the analog inputs. There's timers and all sorts of other things. So that's the memory mapped I/O. And it's sort of put into the same address space as the RAM, because you kind of operate it like RAM. You read to it and write from it as much as you like. I won't be looking at this. I won't be looking at this. I'll only be focusing on the green area. But let's simplify this diagram first. And so that's our architecture. We have the CPU with a bus to the flash for loading program instructions. We have a bus to the memory mapped I/O, which is those I/O registers for like the USART and the SPI and the analog, and then there's the actual memory. And as I said, we typically use these the same way with the same operation, so it kind of makes sense to bundle these together because that's how we use them. And then there's the EEPROM over here. Even though it's sort of considered to be on the same bus as this, I've sort of recreated it like this as more of a logical I/O, but technically this purple bit is over here on this bus. The other thing that I've drawn in here is the bootloader, and that's sort of configurable, but basically it sits at the bottom of memory here. And the reason that's important is because I said there were some rules about how we can write data into this flash, and there's a specific instruction that the CPU executes to write data to the flash, and that instruction is typically only valid if it occurs in this bootloader region. And part of the reason for that is if your sort of program goes haywire, you don't necessarily want to be running random instructions up here that might reset and corrupt the memory. I mean, it still can happen. It can happen that the CPU gets back down to here and it randomly writes something there and you lose the bootloader, or the system just goes haywire, but there are some rules about how the bootloader, how the flash can only be written if you're running in the bootloader. So what that means is you can't use the flash as EEPROM like the ARM Cortex does, but that's just a detail, a difference in the architecture. Okay, so as I said earlier, I'm going to focus entirely on this yellow region here, the SRAM. That's where we're going to be focusing from now on. All right, so drilling into that yellow region, the RAM, that's further broken down like this. So I already talked about the memory mapped I/O, this purplish greyish section at the bottom here. And so I won't really look at that. You can look at the data sheet for how that works. But then the way the C compiler organises the rest of the memory, or the memory, is it uses these sections here. And so then there's these two here, the data and the BSS. So data is for variables that you define in your program and you assign values to them. So here's some examples: int x equals 5, or it could be anonymous variables like this one where there is a value. So we're printing out this string. These things all go into this data section here. The next section is this BSS, or block starting symbol, and that's typically reserved for variables that sort of are initialized as 0, or they're not initialized at all, like these two here, y and buffer. The next section is no init, and it appears from the various linker scripts and so on that this doesn't appear to be used, but typically this is uninitialized variables. So maybe in the olden days, variables like y and buffer would have gone into this uninitialized section, which means that their initial values would be random. But thanks to them being in this BSS section, it's very likely that their initial values will be 0. When we look at that, we might not see that because maybe something has happened inside them. But anyway, that's the idea of the distinction between these two. Then the last one is the heap and the stack. And this can be the source of lots of, why does my program mysteriously fail after 5 minutes of running type questions. And we'll look at this in much more detail as we go. And that's this yellow section here. And basically this is what's left over from all of your variable declarations. So after all your variables and anonymous variables and your buffers and whatnot have been allocated space, and then the no init really doesn't seem to get used, whatever's left over is available for the heap and the stack. And the typical sort of usages of that are local variables. So when you have a function, and if you declared a variable like this, int of x, that would possibly be on the stack. Again, there's rules that determine how that's managed. When you call a function, the return address is definitely on the stack, and when you pass a function parameters, they may be on the stack. Again, like local variables, there's rules about how parameters are passed. The heap, on the other hand, that's completely under your control. So if you use dynamic memory allocation functions like malloc or realloc, or create objects on the fly using the new operator, and some objects that use strings, for example, and I'll look at strings as in capital S-T-R-I-N-G, as opposed to a C string like that, they also use the heap. And then there's a few data structures and things that I'll look at, so linked list, LIFO queues, a stack, and pointers. Now, as I said, I'm going to take a bit of a deep dive into the actual memory on the Uno and maybe a little bit on the 2560. So a little bit of housekeeping needs to be sort of gotten out of the way. And the first one is endianness. So endianness is how values that are more than 1 byte, so an integer or a long, etc., are organized in memory. And so I don't mean strings in this case, that's just a sequence of bytes, but I mean an actual 2-byte or 4-byte value, so an integer or a long. And the endianness refers to which end of that 2 or 4-byte number is closest to 0. So AVR is what's known as little endian. Other CPUs are big endian. I should have looked it up, but I can't think of any examples except maybe the Motorola 68000, which was an older one, I think was big endian. But what little endian means, and that's the important one for this, is that the least significant byte is at the lower address. So the least significant byte is closest to the 0 address in the memory space, and the most significant byte is closest to the top of the memory. So what that means is when we do a memory dump, the numbers appear to be reversed, and that's just simply just an artifact of that memory dumps sort of tend to start at the low memory address and work their way forward, and that has the effect of sort of reversing or jumbling it up. Interestingly, the ARM Cortex can be configured as big endian or little endian. You can research by yourself why that might be a good feature for you. I can't think of one other than compatibility with legacy systems. And if people were sort of doing fancy tricks and things like that that relied on the byte order. So let's look at an example, and we'll consider the hexadecimal value 1234, which would be 2 bytes. Okay, so there's our 2 bytes, 1, 2, I'll say 12, and I'll say 34 just for convenience. So of these 2 bytes, 12 is the most significant byte and 34 is the least significant byte. Why is that? Well, because if we add 1 to this, that only adjusts the number by 1 in decimal. If we add 1 to this, for example, make it 13, then that would change the number by 256. Right, so this is more significant than this one. So this is the most significant byte because it has a greater effect on the actual value of the number. And this is the least significant byte because it has a lower or lesser effect on the actual value of the number. Okay, so because of the rule that I said there, that the least significant byte is a lower address, that means this value gets closer to 0, and this one is further away or closer to the top of memory. And so then if we look at it in memory, then we have it starting at 0, so the 34 would be there, then next to it would be the 12, and so on. And then if we dumped that memory, we typically start at 0 and work our way forwards. So when we look at a hex dump of that, we'll see there's 100, then 110, 120. So then we do whatever that is, 0, 1, 2, and then the third offset. So we'd get to this guy first, so we print that, and then we get to this guy next, and then we print that, and then continue on. So this is not terribly important, but if you can sort of do the mental gymnastics of understanding that 1, 2, 3, 4 would appear as 3, 4, 1, 2 in the memory dump, then that will make the rest of this much easier for you to follow. Obviously, we could extend this. We could do 1, 2, 3, 4, 5, 6, 7, 8, in which case we would sort of see 7, 8, 5, 6, 3, 4, 1, 2 come out in that order. So it's always the least significant byte comes out first, which has the effect that the numbers get sort of kind of jumbled up or a bit reversed. Okay, so let's take a look at this program. So I think what I'll do is I'll just run it. So Arduino Uno, com3, upload it. Just while it's doing that, there's a couple of things about the program. So I'll do a lot in this one tab here, test.cpp. So there's a few tests that I've built into it that I can just run. If you've looked at my previous video about serial command and control, this relies heavily on that. So I created this buffer class that I could use to manage I/O from things like PuTTY and independently of the serial monitor. There's also a command processor, but the most important thing here is that there's these functions in here that can control the operations that I want to do on the Arduino under test. That's uploaded. Let's just start the monitor. All right, so there we've got our program running, and when it starts up, it just simply outputs these segments here. So I'll just bring that back over here. So there's our program, and I'll just overlay that next to this diagram here, and you can see what it's done is printed out these segments. So we've got our data, which starts at 100, so yep, check, and that looks like that goes for 220 bytes. And then we've got this BSS, which is 378 bytes on top of that, and that starts where the data finishes. Then we've got this no init, which, as I said, always seems to be 0 bytes. And then we've got the heap start, which basically starts after the no init and goes all the way to the top of memory. There's a couple of other values here which we'll look at a bit later on, but break val, which is 0, basically tells us where the free memory in the heap is, and then the RAM end is just a constant which tells us what the size of the memory is. If I fire up PuTTY, that's where the mega is attached. And we can already see a difference here. So in this case, the data starts at 200, so it's a bit higher. It's still 220 bytes. It's got the same program running on it. The BSS is 378 bytes, so they're both the same, which is what I'd expect. The no init, again, is unused. And then the heap start basically finishes, starts off where the no init finishes, and it goes for basically up to 8K. So the RAM end here is 8.2K to allow for the I/O space, which looks like it's from 0 to 200 in this case, and then the break val is still 0. So there's a few commands here we can use. I'll mostly use the serial monitor. There is one case later that I might go back to PuTTY. So I think, yeah, I'll just leave that there for now. And so there's a few commands we can enter here. So we can do things like dump the data or the BSS or the sections. We can optionally specify a number. So for example, I can say dump data, or I could say dump data 128 and just get a subset of it. I can also set a dump limit, which I'll look at shortly. And I can also dump a specific memory address. So for example, it looks like we've got a message here at 165. So starting there. So I can say dump 0x165420. And we can see there's the test example. So it's dumping that memory address. What else have we got here? So I can dump the segments. So that just gives us that initial display. Okay, I'll skip malloc and free, but these are to do with using the heap and the stack later on. And the other one, I mentioned that there was some test functions. So I can say test and list, and so it tells me what the test examples are, and they come from here. Okay, so let's look at this. So in this program, which is the INO file, I've got this variable called default output limit, and it's set to no output limit, which is defined as 0xFFFF. If I type in set, then I should see dump limit is set to no limit. And the reason for that is that it's set to FFFF. And if we look at the data, remember I said that a variable that's initialized to a non-zero value would end up in the data segment. It suspiciously looks like that's it there, isn't it? Right, because that's all Fs. If I set the dump limit to 128, and then I said dump data, we should see two things. One is we won't get all of this out. We'll only get about 8 of the rows instead. And we should see that this FFFF has now changed. And lo and behold, it now says 80. So why is it 80? Well, we can use this programmer guy over here. And I think I said, so decimal 128 was our limit. And we can see here in hex, that's an 80. Right? So if I change that to set dump limit 100, decimal 100, oops, clear, 100, that's 64 in hexadecimal, and so dump data, and now I see 64. So this first 4 bytes in the RAM is actually corresponding to this default output limit variable, and it's in the data segment because we initialize it to something that's not 0. If I change it to this, right, so now it's being initialized to 0. So I'll upload that. All right, so I type in set, and we can see the dump limit is set to 0 bytes, so that's goodness. And oops. Oh, I'm getting error, invalid output size. So I said dump data 128. You can see that the FFF has gone, which as we'd expect because we have now set it to 0, but we don't see a 0 there. We see this sort of random stuff here. If I dump BSS, then we probably won't see much. Right, but we do see a bunch of zeros here. Now if I set the dump limit to something else, and then did dump BSS, I can see now suddenly that we've got this 80 here. Right, so that suspiciously looks like our value from before. So let's try 100. And now I see the 64 there. And I can also say set dump limit star, which means no limit. And then we can see we've got the FFF there. So the difference there is that when I compiled it this time with 0, it's gone into this section here. The dump limit is 0, so it goes into this BSS section. Now, the other thing to look at here is that we've got data and BSS is, well, those numbers there, which is 598 in total. So let's see what our output said. It says here, global variables use 598 bytes of dynamic memory. Right, so that corresponds to this. So the compiler or the build process is telling you how much of this space is occupied, which then gives you a way of calculating how much is left over for other stuff. In this case, it's 1,450 bytes, and remember that's used for both the heap and the stack. All right, so just before we end with that, I'll just show you the test commands. So we have these two here. They're defined in this test file. So I've got test list segments, and I can just run this just by specifying the test number. So if I want to list the memory segments, I can do test 0, and that just submits this dump segments command, which is what we've been using here. So we get the same output, obviously. Or I can dump start of RAM, which was dump RAM from 200 for 256 bytes. I can say test 1 like that, and then it just submits that command. So we use that more in some of the other sections as I replace this file. Okay, so let's start looking at the heap and how that works. So now we're going to be looking at this part here. So as I said earlier, the heap is unused memory that we can request for dynamic use. So when would you do that? A good example is the string object, where if we were reading from the serial object a string of input, we don't really know in advance how big it's going to be. So one strategy of dealing with that is to request memory from the heap as the input comes in and just dynamically allocate it. And then once it's processed and we don't need it anymore, you can just release it and return it for something else. There's advantages and disadvantages to that approach. I'm not a big favour of it for small memory systems like AVR. I much prefer to allocate a buffer and limit the input to that size, but that's my preference. The string works differently. Now, when you request the memory, you need to have some way of managing it, and the pointer, that's an important structure. So I've looked at pointers in a few of my other videos. I give a little bit of an explanation of it in my post starter kit and the serial command and control, but we'll look at it a little bit more closely here. If you find this complicated or it doesn't make sense, then maybe have a look at some of those others videos as well. So what is a pointer? A pointer is, at the end of the day, a pointer is a number. And what that number is the address in memory of the thing that it is pointing to. Right? So a pointer is a number that basically says I'm pointing to here or wherever. So go through an example. I've got this variable that's I called it PTR for lack of a better name, and its value is 24A hex. All right. So this pointer is pointing to this address in memory, 24AH. And it just so happens that at this address there's a letter A, and then the subsequent addresses 24B, 24C, and so on also have the letter A. And so therefore this pointer points to a block of memory that contains AAAA. It doesn't have to, the numbers can be random, it could be other values. The content at that location could be other things. It could be hello world, for example. That's not so important. The concept here is that a pointer is a number that points to an address in memory that contains something of interest. So what code would we use to create that? Well, basically you could create that structure using this. So malloc 10 says, give me 10 bytes on the heap, and it returns a pointer. So it returns this number 24AH, and we assign that to the variable PTR. So PTR gets the value 24AH. Now at this point, so this first line of code here, this just contains randomness. So there's nothing in here that's specified. So we initialize it with this function, memset. And what memset is it's a AVR libc memory function. It just sets memory pointed to by this PTR, so 24A hex, with this value and for 10 bytes in this case, so for length 10. So basically it puts the letter A starting at PTR 10 times. So that's how it fills this block up with all of these A's. Now we're not constrained to just doing one of these. We can do multiple. We do need to keep track of each address that we do allocate. But you can actually set up a system like this. So again, in one of the earlier videos I used arrays of pointers. You can look at those. I won't explain that here again, but an array is just a box with multiple values, and they each have their own pointer to something in memory. And so we can set that up using code like this. So we declare the pointers as an array of 10 of them. I've only shown the first 3. There'll be more, but I ran out of space. And then for the first 5 of them, so 0 through 4, we will allocate 10 bytes. So that's these 1, 2, 3, 4, 5. So 0, 1, so pointer 0, pointer 1, pointer 2, pointer 3, pointer 4. And then we'll fill it with this value, so A plus I. So the first one gets A's, the next one gets B's, C's, D's and E's. And again, if you're not familiar with this arithmetic with characters, have a look at the previous video about serial command and control, where I go into explain this a bit more details. So that's how we could create this structure, and because we've allocated 10 of them, we need to store them in an array of pointers. And I'll come back to why that's important later on. Note also that the heap grows upwards, so from the beginning or the bottom of the heap, it sort of grows upwards to the top of memory. So there's obviously a finite resource is the first issue with that. All right, so let's have a look at malloc. I think I'll just reset this first, because that's going to be annoying otherwise. Okay, so we've uploaded it. Okay, so I'm going to be looking at these two commands now, malloc list and malloc size, and then a value. Let's set our dump limit a little bit smaller just to sort of limit how much we get back. And the way I can use this malloc command, I can just simply say malloc 10 bytes and then initialize with this string. So what it'll do is it'll fill the 10 bytes with this string. When it gets to the end of it, it'll just loop back. So we should see AB, 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 AB. And so we can see here is we've issued that command malloc 10 AB. It's been accepted. The address that we got was 358 hexadecimal. So again, these are just numbers that I made up. The actual value we got was 358, and it says malloc address stored in slot 0. So what I have is an array here. Let's see if I can find it. Malloc here, malloc blocks register, and so this thing here is my array, and I've initialized it to malloc blocks size, which is defined as 20, so I have 20 of them. Now, if I say malloc list, then it'll list all of the ones. So remember, this one was here at 358 and it's in slot 0. So we can see here in the malloc list, I've got block 0 to 19, because that's one less than 20. So the 0th one is the 20th one. You can see it's size 10, and here's its content, so AB, 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 and then the rest of them are free. Now, if I dump the heap, and this is where the dump limit is handy, because we can see two things at once. We can see here the malloc block is at 358, and so here's 350, and we go across to 8, which is just after the divider here, and there's the divider, and we can see our AB, AB, AB. So we can see that the pointer of 358 does indeed point to that address in memory, and that it's got those 10 bytes. Now notice at the beginning of it, there's another one here, 0A. Remember, we read these things back to front. So this is 000A. So A hexadecimal is 10. So what this is doing is this is a header in front of the malloc block that we've got, so just in front of the pointer that we have, the 358, and that gives us the size of this block of memory. Now I can malloc some more. So what should we do this time? I'll just do 10 again, and I'll make it a C. So now it's stored in slot 1. We've got address 364, so our AB finishes as the first 2 bytes here, so that finishes there, and then the next one is here, so 364. So notice it skipped the 2 bytes there, right? Again, because remember that's the size indicator, so actual data starts here. So if I said dump heap again, there we can see quite quickly there's our C's and there's our ABs and there's the gap, and we can see this is now written to 000A. So again, we've got 10 bytes, and we could keep doing that. This time it was allocated in slot 1, so if I said malloc list, we can see that clearly that block 1 is block C, and the address and the 10 bytes and so on. Okay, so I think that's all we want to look at from here. Okay, so how do we go about creating something like this? Well, I could type those commands in myself, or I could just use these test scripts here. Okay, so we've allocated the memory. The next thing we want to do is free it. So what I'll do is I'll just upload this while I talk about it. This one has got 3 tests in it. One that will basically recreate this. It'll allocate 6 blocks rather than 5 of 10 bytes each. I'll just upload it. And the next one will free some of those blocks, will release them, and we'll look at how that happens later on. Then it'll be another test that frees another one. So while it's uploading, we'll just look at what that involves. Okay, so as I said, we can request memory as we need it. When you're done with it, the memory should be released. As time passes, though, that may cause gaps in the memory block to appear. And sometimes those gaps are not reusable. I'll look at that in particular when I look at the string and how it works. And this is known as memory fragmentation. The system tries to reuse them as best as it can, but it's not perfect, and you can lose memory, and that can create a problem. So let's have a look at how it works. So starting with this structure, which again is created with code like this, where we allocate a number of blocks and fill them with A, B, C, D, and E, and so on. We execute this command free, and we give it the address of the location we want it to free. So in this case, we're freeing block 1, so that's PTR1, which is 254H. So we're saying we want to free this block here. So it basically marks that it's unusable. Note that it doesn't actually replace it with the words free or anything like that. The content B will still be there. Okay, so that's important. But the pointer to it is no longer valid. It's marked as free, and it may randomly get reused. So you can't rely on it still being B once you've called this free. So that's important to keep track of that sort of thing. If I do another one, free pointer 3, so I haven't got that address here, but that would be, assume it's this one. So that would be 268. So now we've got this one free. So now we've got 2 blocks here that are free, separated by this wall of C's here. Now the other thing to note here is that the free function can't touch this. In other words, it can't modify the parameter, well, or it doesn't modify the parameter. So it doesn't do anything to your original pointer there. But so that means it's not going to change it to anything else. So that means that this pointer is now, while still pointing to this memory address, it's no longer valid because, again, it could be reused by the system at any point in time. So how does it track the free memory then? Well, it uses this thing called a free list. So a free list is a linked list. A linked list is an important structure in computing. It's used in all sorts of places, and this is just one example of it. And a linked list, as its name implies, it's a list of things that are linked together. And it starts with a pointer to some thing. And then the thing that first thing is pointing to also has a pointer to the next thing in the list, which in turn has a pointer to the next thing if there are more things, and so on. And there's a free pointer that points to the first block, if any, and then each free block points to the next, if any. So that's indicated by this diagram. So there's this free pointer, and that's this blue chain here. So it points to this memory location 254 AH. It actually points a little bit before that. And then there's another value in there that points to the next one. So it would point to this 268 H. Okay, and now that we've looked at the internals, remember that this diagram isn't quite correct because it does not allow for the 2-byte header that says how big each block is. So it's more about the concept than the actual numbers in these diagrams. Okay, so we have our linked list. So let's have a look at that shortly. But before we do, I just want to reinforce that if you're using these things, it's important to keep track of the memory that you have allocated and release it when it's no longer needed. Okay, can't overemphasize how important this is. And if you don't do this, how fast it'll be that you'll run out of heap and stack space and have headaches. So lost or forgotten memory blocks are unrecoverable. The system can never use them again until you restart it. They're just there. So let's look at an example. So let's again we'll allocate 10 bytes and set it to the value AA. And then what we'll do is just reuse that pointer and malloc another 10 bytes without doing anything else, and then mem set it to B. So what happened there is the 24A pointer, the value that was there, is simply overwritten with the new value, which points to this new block, 254. But then this is still there. It's still allocated. It's just that no one can see it because we've lost this pointer to it. So basically that's been abandoned or lost track of, and this would never be recoverable until you restart. So if you keep mallocing blocks, you'll just keep building up here and eventually run out of memory. And that would be, again, as I said, a disaster and cause you lots of headaches, because what happens is you get random behaviour. You know, the system will hang, or it might just do random, unpredictable and inexplicable stuff, and it's just try and avoid that. Don't do that. All right, so let's look at freeing some memory. So I'll just go back to there. That one. That one, I think I've uploaded this already. Yeah, so now we have a new set of tests because I uploaded that while I was talking. And they are malloc 6 blocks of 10 bytes each, free blocks 1 and 3, and block 4. So it'll recreate, I think. So I'll leave that diagram there. So what I'll do is I'll just do test 0, and we'll look at what that does. So we can see it here. It mallocs 10 bytes and block A. Then, again, you need to sort of look at my serial command and control video, but this basically removes the last byte from the buffer. So that will remove the letter A and then append a B, same C, D, E, and F. So we should have 6 blocks with A's, B's, C's, D's, E's, and F's. Then it'll set our dump limit. Then it'll run this dump heap command, which I've just set up here because I use it a fair bit. and then it'll run the malloc list, and then we can run some other commands if we decide we need to. So let's just run that. There'll be a lot of output on the screen as it runs it. Obviously that's much quicker than me just typing it in. But there's our heap, and we can see, first of all, we might notice that it starts at a different location. That's just simply because we've got a different program and our data segments are different sizes, because there's more or different data in there. That's all. There's nothing to worry about there. That's just what happens when you compile your program. It just allocates the space it needs for the data and the BSS, and then the rest is left over for the heap. So it just happens to start there this time. But we can see the same structure. We've got 0A, which is our size. Then we've got our A's. So that's this first block, then the B's, then the C's, then the D's, the E's, and the F's, and so on. Got a malloc list here. It's using the first 6 blocks. Remember, start counting from 0, so it's one more than that. So it's 6 blocks, and there they are. And I'll run this command, free list. So what that's doing is it's basically printing this blue chain, right? But we don't have a blue chain yet. All we've got is this free pointer, which is basically saying, well, I haven't got anything in my list because it's set to 0. So there's 0 bytes and 0 blocks available, and the rest of the free memory, 366, starts at 366. So that's basically the end of 366. Oh yeah, the F. So that's the F, and then this is where the rest of the free memory starts from after the heap. So these C's here, I'm not sure where they've come from. Probably from a string object of some kind. I'm not sure where they've come from, but that's just random memory, and we can't use that. Can't rely on that. It doesn't have any meaning to us at all. It just happens to be something that we sort of recognize as a pattern, but it doesn't mean anything. All right, so there's the free list. So the next one I'm going to do is I'm going to run test1, and what that does is sets up a command, and it's going to have free block 3 and fill it with asterisks. So block 3 is this one, which has got the D's in it, and so what should happen is it'll fill it with an asterisk. And remember, the free function doesn't do that. That just happens because I have code in there which frees it, fills it with asterisks before it releases the memory, and then it releases the memory. And then it'll free block 1, which is the one with the B's in it, and then it'll fill that with $signs so we can see it. So there's our memory again. I'll just dump it so it's a little bit closer. There's our memory. So we should see the B's get replaced with a $sign, and the D's get replaced with an asterisk. And then this free list pointer should point somewhere to where these B's are. It'll probably point to this 0A, which would be 33A. Even though we were doing it in reverse order, we're actually removing the D's first and then the B's. The free pointer should actually point to where the B's were, which will be the $sign. Okay, let's give it a try. Test 1. All right, so the first thing I'll look at is we now have block 1 free. So check. Have block 3 free. Check. So that's this one and this one. And so we've got the A, C, and E still there. So we can still see there's A, C, E, and F. That's the F is the others. And now when I look at this free list, we can see now that the free list pointer is 032A. So it's now not 0. Previously it was 0. There it is. And there was 0 bytes in 0 blocks. But now we have 20 bytes in 2 blocks. And those blocks start at 32A and 342. And now we can see the linked list because now we have this next value. So this first block of memory, 32A, which is this first blue one here, points to the second block, which is this second blue one. Remember, these addresses are just random numbers and they'll vary depending upon what your program is. And we can see the heap. So the B's have been replaced by dollars, and the D's have been replaced by asterisks, which is as I predicted. But now let's look at the structure. So we've still got the A's, so we've still got this guy, for 10 bytes. So that goes to here. And we've still got this 10 here, this 0A, and then we've got this 4203. So remember, these are numbers are back to front. So this is 0342. Okay, 0342. So what we have now in our free list is the size of the block that's free and the pointer to the next one. And that's where this 342 comes from. Right, so that's pointing to address 342. So if we look at 342, so that's 340, 341, 342, we have a similar thing. We've got the 0A, so that means this block is 10 bytes long, and our next pointer is 0, which means there is nothing there. And as I said before, I just filled it with asterisks so we could make it a bit easier to spot in the dump thing here. Now this B here, you might say, well, that's the B from before. No, it is not. It's just a coincidence. Again, if you look at my previous video about serial command and control, you'll see that a letter B is just a number, and we can interpret that in any way that we want to. And it just so happens that the pointer to the next one is 342, which is here. And it just so happens that 42 happens to be the ASCII code for a letter B. So it's just completely, totally random that this B is still here. Okay, it has no relationship whatsoever, because this is now an address, but when I'm dumping this, I'm interpreting each byte as a character for printing, and that's just completely coincidental that we get a B there. When I rehearsed this before, I had a slightly different structure, and it wasn't a B. But now it just randomly is, which is unfortunate. Otherwise, I probably should have used a different letter there in the initial buffer. The other thing here is the free list pointer, which I referred to before as the break value. Right, so now we have break value is 366. That's pointing to where the rest of the memory is. Okay, so that's not actually the break value. There must be another one that's pointing to the first object in the linked list, and I haven't tracked that down. So this is pointing to when you get to the end of the chain, so the end of this list here, that's pointing to where the next location is. So basically it's pointing to the top of this line here. Okay, so if we allocated something larger, it would get there. What's test2 do? I might explore that. Yes, I'll do this first. So what I can do is say malloc, this time I'll do 16 bytes, and what should I make it? A G. Right, so we can see the G's have gone there. Our break address is 368, so 368. So that's where it starts at. And then it's put the size there. That's 10 hex is 16. So there's our buffer. So 368 is where the next one goes. And the reason it went there is because I deliberately requested 16, and 16 won't fit in there, and it won't fit in there, and it can't split it, so it has to put a new one up here. So we're already looking at fragmentation. But now what I'll do is I'll run test2. So what test2 does is that frees block number 4. Maybe I should. There it is, test2. Frees block number 4. So note that we've got block 3 is free, and then block 4 is next to it. So what we'll have is block 3 free and block 4 free. And so they were contiguous previously. So block 4 would be this one. Is that right? 0, 1, 2, 3, 4. Yeah, this one. So we have 2 neighbouring free blocks in memory. And so we'll see what happens. Can you guess what might happen? Let's find out. So it frees block 4 at address 350. So that's this one, which had the E's in it. And we're going to fill it with hashes. So now we have hashes at that, or pound signs if you prefer, here. We can see it's next to the asterisk as I predicted. And now, so what's happened is this one with the dollars, the first one we freed, which was previously block 1, that's still 10 bytes, and it's still got the C in between it. So that's this scenario here. But because I've freed this one, which is next to an already free block, rather than creating another pointer to it, it's just extended this so that this is one larger block now. So let's see how it's combined them. And you can see that here because now it's 22 bytes. It's the original 10 bytes, plus it's the 10 bytes from the whatever letter was there before, the E, right? So that's 20. But there was also a 2-byte header, right? So there's this guy, 0A, these guys, that weren't counted as part of it, but they're now no longer needed either. So it's the full 10 bytes plus this header can be combined into the lower free block, meaning 12 bytes gets added to it. The 10 bytes of the data and the 2 bytes of the header, which is the record size. So now we have a 22 free byte block. Now, if I tried mallocing a smaller buffer, so let's say malloc 6, and so I'll use H this time. Then can you guess what might happen, where it might put it? So the options are, will it put it at the end on top here, or will it try and use one of these? And if so, which one will it try and use? So let's find out. So I've allocated it. So it looks like it's put it at address 330 and it's used slot number 3. I should point out, I should have done this first, but yeah, these slots are my pointers. The index is into my pointer array, and so there's not really much relationship to these free blocks. So that's just which pointer address it's used, and that's the first one that it used. So if I dump the heap, we can see our H's have gone into this first free block here because that had 10 bytes available, and 6 can definitely fit in there. So if I run the free list, then we can see now we have 2 bytes left because we've taken 6. There was originally 10. We've taken 6, but we also need to add 2 bytes for the header that says how long it is. So that's 8. So that leaves 2 bytes in this one, which basically means this one is now unusable. So that's here at 32A, which is here. And we can see there's 2 bytes. And then there's the next pointer, so 342. So if we did allocate 2 bytes, they're the bytes that would be used because we still need this for the header size. So 342 is the next one, so 3402. So there's a block of 16, and remember this is hexadecimal, so 10 is 16 bytes plus another 6 is 22. So that's where 22 comes from. And then we have 00 as the pointer to the next address, so that's the end of our list. And then if we had any more, that would go there. So if I allocated something that was less than 22 bytes, then it would go in this block here, not at the end. So I'll just come back and clarify this a little bit. Basically, there's 2 values that are used to track the free list, and I was showing them in my output. Not so much the dump segments, although I have added it now here. So there's a free list and the break value. But it was always showing here, so we had this break value and the free list pointer as 0, which is how it starts out. But I'll just show how these 2 work. So this is the new part. The break value serves to points to the first unused byte on the heap. So there's our free pointer, which I had before, and then there's this break value, which points to the top of the memory. So it's the first free byte that is available after malloc is first used. So let's just have a look at that. So initially they're all both 0. So as I said, I've added it here. So the free list is 0, meaning it's empty, and the break value is 0, which means basically nothing's been allocated on the heap yet. So we just basically start from the top of the memory, which is this 31E location. So if I allocate something on the stack, so I put a Z in it, then that's been successful, and we can see that it's used the 320 location, which is basically the start of the heap here. Now we can see that the break value has been set, so that's basically pointing to the first byte of memory after this. And we can see the free list pointer is 0, meaning there's nothing on the free list yet. So this blue structure doesn't exist yet, but our break value has now been set, so it's pointing after our memory. And so we can see that here. There's our Zs, and the break value is 32A, so that's pointing to the first byte after the last of our Zs. I think that's just random that it's like that. There's our length as before. So I've got the malloc set of tests available, so I just run test 0 and dump our segments. So still our free list is 0, but our break value has now moved up quite a bit. It was what? It was 32A, but now it's 372, and that's just to allow for the fact that it's got these extra things available now. And so we can see here, this is our malloc memory that we've got out of our test, and the last memory, or the first unused byte, is after this one, 372, and so that's what that's pointing to. If I dump the heap, we can see that in a different light. So 372, that's the first byte after that. Alright, so what I'll do is I'll now free the fifth one. So let's see, that would be 1, 2, 3, 4, 5. So that'll be the Ds, I think. And we'll put a star in there. Let's just have a look at that first. Oh no, so sorry, it was the E's. So what we should see now is this free pointer has now been established, and it should be pointing to the first free block of memory, which would be, well, I guess this one, whatever. It'll be pointing to one of the free blocks of memory. Now, we haven't done anything with the break value, so that'll remain the same. Right, so we can see now we've got a free pointer, and the break value is still 372. So the top of memory, 372, is still here. That hasn't changed because it just opened up a little gap in the middle. And now we're starting to have a linked list. So we've got this free list pointer is 35A. So that is pointing to here, 35A. So we have a block of 10 bytes, and the next pointer is 0. So there's no next pointer. All right, so I'll free another one. Let's see, I'll put, I think, $, in it this time. And so now we've freed up this 32C. 32C, so we've freed up this one. So the A's will now be replaced by the $sign. So dump the heap. Let's make that a bit bigger. So we can see there's our $signs in place of the A's. We can see that our free list pointer, I think, is changed. So it is now 32A. Previously it was 35A. That's because I've freed up this one, so it's inserted in the beginning. And our break value is the same. And then we have 2 entries on the heap. So hopefully that makes that a little bit clearer, that there's the 2 values, the free list pointer and the break value, which I was always showing on this screen, but I wasn't showing the free list previously in the segments. So hopefully that was clear. If not, by all means, leave questions, and either on Reddit or in the video, and try and best answer it. If it's a complex question, Reddit might be a better place to ask. I do include my Reddit handle below, so you can ping me there if you do something. Okay, I think that's probably all I want to show here. So let's switch gears a bit and we'll look at the other side of this equation, the stack. And spoiler alert, these arrows are pointing at each other. So just bear that in mind. Okay, so the stack is temporary storage used by functions when they're active. There are some other uses like interrupts and things like that, but primarily it's used by functions. It has a few different, I guess, scenarios of use. So one is for variables that are declared within the function other than static variables, parameters that are passed to functions, the return address, and all of the above are subject to rules of when and how they can be used. And these rules are more to do with optimizing calls. Return address is always passed on the stack. Parameters and local variables may be declared on the stack. It depends upon what they are. If you want to find out more details about this, have a look at the mixing assembly and C with AVRGCC, which is a microchip tech note or application note, and that's the number there. So you can Google that title and you can find out all sorts of nitty-gritty technical details that cover aspects of how the stack is used for function calls. All right, so like a linked list, a stack is another important data structure in computing. It's also known as a LIFO list. So LIFO means last in, first out. So think of like a stack of plates. You pile them up. The last one that you put on is typically going to be the first one that you take off, and so on. And so that's what that says there. The value most recently placed on the list or the stack is the first one to be retrieved. So I'm only going to look at the CPU stack. Every CPU uses them. They're a fairly important concept. They typically work the same way, have the same concepts, and those are that it's a contiguous block of memory in RAM. It's managed by a stack pointer, often abbreviated SP. It's operated via push and pop operations. In this case of the CPU, we don't really always see a push and a pop instruction, but that's the operation that's known. So for example, we might see a call operation that will push a value onto the stack, and we might see a return operation or instruction in the CPU, and that will pop a value off of the stack. And so push and pop are the generic terminologies that's used to define how we manipulate the stack. And in this case, the SP or the stack pointer is a special purpose CPU register that's sort of designed to work with those instructions and help maintain the stack. And as I say there, a stack can be based upon other structures such as the linked list. So you could use different structures to create this LIFO list. All right, so there's our architecture diagram. So we have the CPU. It's got a specific register called the stack pointer, and basically that points to in the case of AVR, the next value that we're going to use for the stack. So here's an example of it. Starting with an empty stack, which is basically powered on, and set the stack pointer to point to the top. We might push a value 1. And so we have this value 1 placed at the top of the stack, and then the stack pointer points to the next location where the next value is going to go on. So we push value 2, same thing happens, we get value 2 written to the stack, and then the stack pointer is incremented to point to the next location. And so that just goes on and on and on. So the next interesting thing is, well, what happens when we want to take values off? So we pop it. We do a pop operation. So value 2 effectively comes off. The value is still there, it's not overwritten, but the stack pointer is moved back up to point to that value. So I'll just go back and do that again. So I've got the CPU pointing to where, if we kept going, value 3 would go. We issue the pop operation, so value 2 effectively sort of comes out, and then the stack pointer moves up to there. If we popped again, then the value 1 would come off, and then we point to the top again. Okay, so let's have a look at that. Let's get rid of that and put this in here, and we'll turn on the serial monitor ready to go. I think I'll just go back to here. Yeah, that'll do. And upload that while we're talking about it. While that's uploading, I'll talk about this. So this This one only has one test function. I probably shouldn't have the comma there, but it doesn't matter. And what this does is it does a recursion test. So recursion is where a function calls itself. So in this case, it's not doing anything terribly exciting. It's just calling this function recurs with a parameter 0. So just make sure that's worked. Yep, recursion test with stack dump. Okay. So recurs 0. And so here's the recurs function. So it's just a regular C function, nothing special about it. But the key thing here is this. So the parameter passed to it is level. And what it's doing is saying if the level is less than 5, so 0, which is what it started out as, then I'm going to call myself again, but increment the level. So when we first come in here, we're going to recurs, it's going to be value 0 as courtesy of this initial sort of startup sequence. It's going to copy something into this thing called work buff, which I've declared here. And remember before I said that a local variable and a function will be declared on the stack. So we'll look for that as one of these value 1, 2, 3 things. And it'll copy something into it. Indeed, it'll just copy something from this array here. So 0, 1, 2. So if its level is 0, we should see 0. And then when the level is 1, we should see 1, and so on. Then it'll just print out a message showing that we're in here, and most importantly is it'll output the stack pointer value. So we actually get to see this value. And so then, as I said, if the level is less than 5, which it will be the first time around, it'll be 0. So it'll call itself again, but it'll add 1 to it. So at this point here, right, so at this point here, in the middle of this statement, we go back up here, and now level is 1. So it's going to allocate a work buffer. It's going to copy numbers at level, which is now going to be 1. Then it's going to print another message, and note it prints this pad spaces level. So what that does is print out some spaces according to the level. So we should see a nice indented output. And it'll come down here, and level is 1. Right, so that's less than 5. So it'll call itself again with 2 and just keep doing that. So we should see this output sort of saying, you know, I've entered level 0, then slightly indented, I've entered level 1, I've entered level 2, I've entered level 3, then I've entered level 4, and then it'll call itself again. So now it'll be level plus 1, which is 5. So it'll come down here and it'll say, I've entered level 5. This won't be true anymore. So now it'll go down here. So then what it'll do is it'll basically dump the stack. So we'll see a stack dump at this point. And then it just returns. So what happens when a function returns? Well, it comes back out of here and then executes the next statement. So we should see returned to level. And once it prints that message, then there's nothing more for it to do. So it'll return. So that means it'll come back to here again. And so what we should see is it unwind itself. So here we should see messages saying entered level 0, then entered level 1, entered level 2, and so on, until we entered level 5. Then we should see a stack dump, and then we should see returned to level 4, returned to level 3, returned to level 2, and so on, until it gets back to level 0, which is where it'll come out here. All right, hopefully that makes sense. If it doesn't, just rewind the video, pause it here, try and follow through again what's going on. But the key thing here is it's calling itself. And each time it calls itself, it's going to use more of the stack because it needs to remember at this point where to come back to. And then the same for this one when it finishes this block. So I guess that's there as well, or maybe it's there, whatever, however you want to think of that. It's finished doing this aspect. It also needs to know where to return to, and eventually when it gets to the top level one, it's not going to return back to here. It's actually going to come out here. Okay, so let's give it a shot. It'll happen very quickly, but I'll try and walk through it. So there's only one test in this, test 0. So here's where it starts. So it prints out our message recursion test with stack dump, and we can see here it's entering the level. So 0, that's this work buff, and that comes from this array here. So we get 0, 1, 2, 3, 4, and 5. So there's our thing, there's our messages. And you can see here that the stack pointer is increasing. So, sorry, decreasing, because it grows from the top downwards. So for whatever reason, when we first enter this function, there's already some 40 hex 4B, I think it was going to be 4D bytes on the stack above us when we start. And we can see it sort of incrementing or decrementing by 10 each time. So we can see the memory is getting, or the stack pointer is getting further and further, or closer and closer to 0. Okay. So we'll dump our stack. And in this case, again, because we start printing from the bottom, we're kind of going to see it in reverse. So if we were going up here in this diagram, we'd see value 2 first, then we'd see value 1. And we can kind of see that here because we've got that text. This is the work buffer. So we've got 5, 4, 3, 2, 1, 0. And you can see here I do this mem set. So I have this work buffer here of size 10, and so I set it to all asterisks. So I explained the mem set function before, uses the pointer, which is what that is. Work buff is simply a pointer to a block of 10 bytes. I set that pointer to asterisks for a count of 10, which is what size of returns. It returns the size in bytes. So that's why we have these trailing asterisks here, and we get this nice block of 10 with the asterisks overwritten, courtesy of this string copy. So the string copy will copy one of these variable length strings into that buffer. So that's why we have 0 dot asterisk asterisk, 1 dot asterisks, 2 dot asterisks, 3 dot asterisks. And this dot here is simply a null. So again, I keep referring to it. If you look at the serial command and control, I talk about this null. It's a convention in C that null means that's the end of the string, or it points to nothing. It's the end, and we saw that in the linked list as well, where the last element in the list had a 0, 0 byte, meaning the pointer was 0, which meant there was nothing further for it to point to. So that's an important concept. Okay, the next thing we see is all of them have this 0BF7. So we've got 0, so we've copied our 0 in here, and then we recurse. So when we recurse or call a function, the first thing that goes onto the stack is the return address. So what that means is that the return address here, interestingly, is 0BF7. So this is sort of reverse order, because F7 0B would be an invalid flash memory address, I think. 32K, yeah, that would be an invalid memory address. So it must be BF7. So it uses a different endianness here for the return address, I suspect. Anyway, that's not terribly important. The important thing is that this is the return address, and we can see for each one of these it's 0BF7. Now for number 5, we don't actually call recurs again, we actually do something different. We do this command stuff. So that one's return address is going to be something different, because it's going to come down to here. Yeah, it would be coming back out to here, I think it is. So that's completely different, because that could be anywhere. Then there's 2 other things that we can see on the stack. Now, one we can recognize. So there's our 0, there's our 1, there's our 2, there's our 3, there's our 4. And basically that's the parameter that's been passed, but it's the parameter from the previous function. So remember I said there's rules about passing parameters and local variables onto the stack. The CPU tries to use CPU registers for parameters and local variables when it can, and so the compiler has decided that it's going to use a register for keeping track of the level inside the function, as opposed to passing it as a parameter. So what that means is that if the compiler's decided I'm going to use a CPU register for tracking the level here, I need to preserve that register before I do anything else. So immediately when the function is entered, it's going to preserve the current value, which effectively is the previous level's value. So that's very complicated and confusing, but it's not relevant, not terribly relevant. The important thing is here that this is the level of the previous function. We can also sort of see that the 5 is preserved up here. The pattern is different because basically it's a different function that's required to preserve it, and that's the submit command. But we can see what looks like the 5 there. What else? And then there's this 813, 823, 833. So I'm not exactly sure what this is, but it's the same idea. There's a variable that's used for some temporary processing in here. Maybe it's for the arithmetic here or this comparison, but the point is that the compiler's decided it's going to use a CPU register, so it needs to preserve the value that was in that register before it does anything else. Okay, so this is the disassembly listing of the code, and so here we have this void recurs int function, and you can see the very first thing that it does is push these registers onto the stack. So there's no code in my function that does any of this, other than the way I've declared some variables. But the first thing it does is push 4 bytes. So R16 is register 16, R17 is register 17. So those two combined make up the integer that's the level, because an integer is 2 bytes and registers 1 byte. And it pushes R28 and 29, and the reason it does that is because it reuses those, and according to the rules in that tech note that I referred to before, the callee recurs must preserve those registers if it's going to use them. And then it does some other stuff here. The main thing that we're interested in here is that R28 and 29 are the stack pointer, and then you can see here it's subtracting 10 from it. And then it writes it back out. So that's allocating the 10 bytes on the stack for this work buffer. It just simply does a subtraction to allocate that space, and it's not initialized, so it doesn't need to do anything more than allocate that space. So that effectively would be an uninitialized storage. And then lastly, as I said, we do this recursion, so that's caused these messages to appear, entered level 1, 2, 3, 4, 5, suitably indented. And then once we've finished, so we've gone down this path and done the stack dump, which is what this one is, then we unwind that call tree. So basically now what it's doing is it's removing all of this stuff from the stack. I won't show you the code there. If you're really interested, you could do this yourself. And then it's returning, which means the PC is set to this address. So it's set to BF7. But remember, it's restored this value before. So if we were to use level here, returned to level work buff, then we get the correct value coming up because it's restoring this level stuff as we go back. So we get the 4, 3, 2, 1, and 0 as it's printing out the correct work buff, courtesy of these two statements of code. And then eventually it's got back to the bottom one, which is this 0 here. Then the next return address is B8C, or actually probably 8C0B, B0B8C, which basically is here. So then we return from the test 0, and then that's the end of the process, the end of the test. Okay, so previously I did sort of allude to the fact that these two arrows are pointing to each other. Maybe you figured out the trick or the issue, maybe not. This is a phenomenon called a stack heap collision, and basically it's where the stack and the heap try to occupy the same memory locations. So this is not a good thing. As I said before, after we allocate our data and our BSS, the heap grows up from the lowest address, so the first free memory available address, and the stack grows down. So just in case these two arrows pointing to each other weren't very clear, hopefully these ones are a bit clearer, because eventually you could get a situation where they overlap. And like most collisions, it's undesirable and they're difficult to predict. Things are allocated dynamically, they grow and they shrink. If you have fragmentation, then you might calculate that you're only using X, but in reality, because of the fragmentation, there's sort of like a tax on the X, and it's sort of actually X plus a percentage, and that percentage may grow over time as the fragmentation gets worse and worse and worse. And so depending upon how well you manage this, and indeed how well you manage this, you may or may not get this collision. And so we'll look at briefly what happens there. And then we'll pose a question about what can be done to deal with this. But let's look at it first. So I'll use the same structure, the same program that we had before. So not that one, this one. All right, so I've still got this recursion test with stack dump. So it's basically this guy here. And what I'll do is allocate some memory. So right now I've got nothing on my heap. So my heap is empty. So basically the stack has got free reign to use as much as it likes here. So we've already done test one. We can see that it does its thing. I won't bother running that again because we just went through that. But what I'm going to do is I'm going to malloc 500 bytes and I'm going to fill it with an A. And the only reason I've done doing it in 2 segments is because I have actually set up a limit that says I don't want to accidentally allocate too much memory. If I say malloc 501 or 601 and then B, it'll say, sorry, you can't do that. The maximum is 500. And that's just to sort of avoid me having an accidental typo and did something like 5 million or whatever, and that would be undesirable too as well. So anyway, malloc 500B. All right, so there's our 2 blocks of 500 bytes. So basically we've used half of the memory right now. Half of the, or in fact probably more. Yeah, so I've used fully 2/3 of it. There's 1,436 bytes available, and we've effectively used 1,000 of them. So the important thing here is I'll dump the heap. All right, and we can see that stuff is there. There's our A's, there's our B's, and then there's some space available here for some other stuff. So now if I run test 1 again, test 0. All right, so there's our output from our test. We've dumped our stack, and somewhat worryingly, we can sort of see some B's here, but maybe that's okay. But let's dump heap, and so that we can see there's our A's, and our B's look a little bit not so healthy. If we do a malloc list, we can see our A's are okay, but there's all this gibberish here now in our B's. And the reason for that is that we've had a stack heap collision. Now in this case, what's happened is I boosted the heap up quite high, maybe let's say to here on this diagram, and then I did that test, and that called the stack down to here. So we have this overlap here where the stack has overflowed into this heap. Now in this case, it's not a disaster for this particular program because I'm not actually doing anything important with this. But if you had some important data in here, like, I don't know, maybe you've got a JSON file from some online server and you've stored it on the heap for the dynamic memory allocation, and then you've executed a bunch of functions that dive fairly deep, then now your JSON is corrupted. Your string contents is just corrupted. It's overwritten with all of this gibberish. Okay. Now the other thing to consider here is, where do we call it? Here we go. So this recursion function, we can see it's got this return to level work buffer, and we identified that here each one occupies the 10 bytes for the buffer, 2 bytes for the return address, 2 bytes for the previous level, and 2 bytes for whatever this working thingy is. So that's 10 plus 3 lots of 2 bytes, so that's 16 bytes. So each call occupies 16 bytes. And we can see that this has gone way, way higher up into here. So our call here goes to 800, but when we look at this, 800 is where our calls to recursion goes, but still it's been corrupted all the way back up to here. And the reason for that is because we're calling these other things. So the mem set, the str copy, the pad spaces, the serial.print, this print address function, they're all calls to functions, and they also will put a return address onto the stack, and they also will create their local variables onto the stack and push any registers they need to save onto the stack. And so even though we saw that our recurs function only really goes to this 800 address, all of those others are doing the same thing, and they also require the stack, and so it's gone all the way up to here, and that's where the corruption occurred. Now, if you did it the other way around, so if we allocated a third block of 500 with C, okay, so we allocated the third block of 500 bytes, that would mean that we've allocated 3 times 500, so we've allocated 1,500. So what that means is the heap will have grown all the way up to here. In fact, it would have overflowed the top. But the main point is that it's overwritten this. Now in my case, I use the stack to overwrite the heap, and I don't really care about the heap because it's just test data. But if we did it the other way around, and the heap grew so that it overwrote the stack, then guess what would get corrupted? This stuff would get corrupted, including the return addresses. So what that means is that the CPU will continue executing instructions that the program counter is pointing at, but eventually it's going to get to return, and it's going to take the value, whatever value happens to be there in memory, and put that into the program counter and then start running instructions from there. Now if I filled this with A's and then B's and then C's, then that would be, well, a CC, which is a 43. So the return address would be 4343, which would be invalid, right? Because here's a C here, and that would correspond to this value here. So if we fill this buffer with C's, then all of these would be C's, and so now the address would be 4343, and that's invalid, and definitely random, and that's where unpredictable results occur from. Okay, so that might sound a bit scary, and when it happens, it's really annoying, but it's just something you need to be aware of. And if you do get random behavior, try and understand that this is what's going on, this type of thing. It could be the reverse. I mean, it could be that you have meaning in here, and in your code you're expecting this to be a 2 B's, but really it's a dot and a 2, so that would be this D132. And so, like, what the heck is that? Where did that come from? I don't know how to deal with that, and you might expose other bugs in your program that might cause undesirable results and random behavior. So you can get it the other way around, but as I said, I don't really care about this. I've just set it up for the test data, and that's the reason why I've done it that way. So I posed the question, if we do allocate data on the heap, or we do have big call trees, really we want to make sure as much of this memory is available as possible to give it the maximum opportunity to sort of manage things safely. So how can we do that? Well, there's really only 2 options, and that is to lower this line in memory as best we can. And if we lower this line, well, I guess this no init line, but since this always seems to be 0, it's basically the same line as the BSS. If we can lower this line as much as possible, then we'll give more space to the stack and the heap, because it just uses whatever memory happens to be left over after these things have been allocated. Alrighty, and so that's the question that I pose here. What can we do about this? Well, as it turns out, there's heaps and heaps and heaps of things that you can do. Here's some of the, let's say, the low-hanging fruit strings. So I'm going to pose a question here, and what I'll do is I'll switch over to the Mega and repose this question. Okay, so I set the dump limit to 128. And remember, this has got the first set of tests in it, which just simply, I haven't bothered to update it. It's the little initial demonstration where it dumps the memory segments through. So if I ran test 0, then we can see it has this executing test 0, test example, list memory segments, and then it prints these segments out. I don't think I've got anything on the heap just yet. Okay, so malloc 10A, malloc 10B, that'll do. And so we can see we've got those things in the memory now. If I said, did I set the dump limit? Yep, dump heap. So we can see those values there, and there's an appropriate amount of randomness there as well. And I'm going to do dump data. I'll do star so I can see the whole thing, and I'll just run this again, and so we can actually see test example dump RAM from 0x200. So we can actually see that message there in the RAM. This one, test example list memory segments there. And then there's also this word here, dump segments. Oh, that's because test 0 actually does that dump segments command. And so I see those strings. So then the question is, well, where does this come from? And indeed, this, where does that come from? I don't see that there. So just hold that thought. The other thought that I'm going to give you is, well, how does this get here? Because remember I said RAM is volatile. So if I switch the Mega off, which one is the Mega? This one. Then the first thing that will happen to sort of demonstrate that is that I got this error reading from serial device. That's because the Mega has got turned off, and so it's lost contact. So if I turn him back on, right, now I can restart the session, and the reason I'm using putty here is because if I did this in the serial monitor, I actually have to close it and reopen it. And of course, when I close it, I'd use this, I'd lose this, let's call it evidence. So restart the session, and now we've restarted it. And what I'm going to do is, first of all, I'm going to do is set dump limit 128 before I forget, because I don't want the heap to scroll everything off the screen. But I'll dump the data. Right, so we can see that everything's there. So that's cool. Everything's come back. But what about, where are they? What about these guys? If I dump the heap here, I've got the A's and the B's, and then there's some random data. I'll just pick something afterwards. So I've got 6A859C. And we just happen to have 6A859C there again, but we certainly don't have the A's and the B's. So that's been lost. So why is that? Well, the answer is RAM is volatile. So then the question is, where do these come from? How does it know to put these values in here? Indeed, how does it know to make this dump limit FFFF, which I should have dumped? Well, I'll just reset it again. Start. Dump heap. This time I'll limit it on the command line. Sorry, dump data. 128. Right, how did it know to make this FFFF? And the answer lies, oddly enough, in this distinction here. And all code and initialized to non-zero values exist in the flash. and we already determined the flash was non-volatile. So what happens is, before the Arduino code, our C code is even invoked, the C runtime copies a block of memory from the flash and copies it into this data segment here, right? So it literally is a copy. So there's let's say this was 80 hex bytes. There would be a block of memory that's 80 bytes in size in flash that contains the contents of all of these initialized variables, and there's a small section in the startup of the runtime for the C that copies that 80 bytes, or whatever the size is, from flash into this memory segment. Okay, so it copies it from flash. So this data comes from the flash. This guy, values that are initialized to 0, there's just a little loop in that same runtime that basically says, starting from here, just make the whole thing 0. Right, so copy this block of memory from flash and initialize it to the contents of flash, so we get all these weird and funky values copied out. And then after you've done that, just set this lot to 0. That's what the runtime does. And that all happens before our code is called. So one way that we can increase our space is moving those strings to the flash. Right, so again, I pose the question that we can see this message, test example list memory segments, here, but not this total 2 tests. Just observe here that we can see that the strings here are the ones that the print line is using, and those are the messages that we could see in the putty, as was that one, and these are just taken from memory. So if I said dump data, we can see those messages again. And the important thing here is we can see that there's 220 bytes being occupied by the data. So that's those 220 bytes, pretty much half of which is just these messages. Okay. So then I pose the question of, where did those other messages come from? Well, if we look at this, we'll just look at the usage one. You can see what I've done is I've put this F function around them. And so what this F macro means, and it's a little bit sensitive as to what you use, so it's a little bit technical and a little bit subtle. But what this F thing means is, don't bother copying it to RAM. Right? Just leave it in flash. That's what this F means. So leave it in flash. So what I could do is I could wrap all of these in flash. So leave that one in flash, leave that one in flash, and I won't do anything with this one just now. So I'll upload that, and we'll just note that we have 220 bytes in data and 378 in BSS. So what I should expect to see is that this won't change, because I haven't sort of changed any variables that are initialized to 0. But I'd expect that this one should drop down, because these ones that are effectively non-zero, they're anonymous variables, but they're non-zero, they should now be left in flash, and so our data segment should drop down. And so there we have it. Previously 220, now it's 134, 378, that remains the same. And I confused myself. I thought, why is it lower? I was looking at the other way around. And so now we've got that extra space allocated to a heap. So we've got another, what, 100 and, not quite 100. So we've got another 86 being the contents of these. So if I dump data, we should see that that's shorter, and we see that those messages are gone. Looks like I've missed one. And I've missed 2. So I've missed that one, and I've missed that one. I said I'd come back to that. So I'll just do this one, and now what we should find is we get an error. And this is what I was saying, it's a little bit technical. Oh, I'm shocked. Okay, so that's test 1 that I changed. Let's see if it works. Yeah, it didn't work. And the reason for that is because I moved this into Flash, it's not understanding that the address that's being given is in Flash, and therefore it needs to use a different set of instructions to extract that memory. And so this goes back to, and yeah, so it doesn't understand that it needs to use a different set of instructions to go back to memory. And this goes back to that these addresses are reused. So we've got a 100 here. Let's say the string was there. There's also a 100 here. So when we're copying the data from the pointer that's given to it, let's say it's 100, if we use the F macro, then that function that's appending those characters, so I'll just bring up the code, hopefully make it a bit easier. Yep. This append function needs to know that that address is actually over here and use different memory operations to copy the data from here. And for this particular this buffer, I haven't bothered to do that, but I think I probably will add that in. So here's our declaration of the buffer here. It just simply says append const char str, and it's trying to use this, but it's copying data from a random location in memory here rather than where it actually is in the Flash. So the serial.print line understands that distinction, and it recognizes that this F is being used, and so it will take the data from this Flash over here. I think I have one example here. Here's one example of the difference. So these two function signatures are basically the same. Let's move that over to there, like that. So you can see these functions are exactly the same. The difference is that it's got this thing here called const flash string helper. So this print address function can take an address from data in memory, which is this second line here at line 13, or it can take an address from Flash, and that's at this line 12. So if I use the F operator for calling print address, then it would use a different version of the function. And so if we look at those two things, print address, they're here. Right, there's the first one. So this is the flash string helper variant, and I already said that serial understands the distinctions, so I can just call serial print with the message and it'll do the right thing. Ideally I would put F in there as well, because that's an unnecessary space that's occupying memory, and the same here. Don't need that. Whereas if I just use a regular character string, then it would call this variant, and again, serial.print understands the difference between those two. So that's how we can do that. There are other functions as well. And this is what I mean by it's a little bit technical and nuanced. So in the memory, we didn't see there's these dump or limit or any of those other commands that were in the RAM. And so the AVR libc provides some functions. So again, referring back to the previous video about serial command and control, you would see I used str case compare to work out what command is being executed or submitted by the user. I just left these things in the RAM, and so that's maybe not such a good idea, as we've discussed in this video. So I can say, well, leave it in the flash memory or the program memory, which is this red one over here, by using pstr. So that means mark this dump string as something that just gets left over in flash and not moved to RAM. But because I've done that, I need to use a different version of the function, and where the string is in RAM, I'd use str case compare. The way the AVR libc is structured, I need to use str case compare underscore p, and what that means is it'll compare a value in memory, so that's the value that's been entered by the user. Obviously the value entered by the user is going to be somewhat random, so that can only be stored in RAM, and it's going to compare it to this fixed message that's in the flash. memory, and so that's what this one does. So again, it's a little bit subtle, but as you can see, if we use this, at least use this F operator, which won't work for here unless I add a flash string helper version of it, we can save ourselves some memory and give that to our heap. And so if you have a big program with lots of print messages or strings like this, particularly in serial print statements, an easy low-hanging fruit to get more memory available for your stack and your heap is just to whack this F around them. It's a bit tedious, but it's a great way to save some memory. As I saw before, we went down to 134 bytes from up here where it was 220. All right, so what else can we do? Okay, so balance stack and memory allocation. So let's go back over here and I'll reinstate. So I've just reinstated the recursion one, recursion test with stack dump. We'll just let that upload. We'll just let that upload. And so one thing we can do is balance how much stack and global variable declaration is required. So an example here is work buff size. Is that optimal? Is it even required? So let's again, that's uploaded. That's our memory. There's our test. And so we can see here each call occupies the 16 bytes. So I looked at that previously. So that's these, well, it's these 16 bytes, I guess. So we've got the work buffer, we've got the previous level, and then we've got the return address. So we have no choice about the return address. The system needs to track the return address. There's no choice there. But look at the work buffer size. I've declared it at 10 bytes, but it never uses all 10 of them. There's always some asterisks left over. So maybe we could reduce the size of that a little bit. And that's going to be especially important if we call recursively quite deeply. What else did I put there? Do we even need work buff? Is it required for this example? What do you think? Anyway, I'm going to give you the answer. It'd be nice if you left your answer, what your thought were in the comment, be honest. But do we really need it? And the answer is no, because what we're doing is we're allocating this string on the stack. We're filling it with asterisks. Then we're copying a value from this array based upon the level. So we've got this array, which is already indexed by the level. We're copying the data from here into here. Oh, and by the way, we should be able to see those things on the data. See, there they are, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can see those on the data. So they're already on the data as well. We could put these in Flash, and we could use strcopyp, whatever, but that's not the point here. So do we even need this thing? Well, no, not really, because all we're doing is we're printing that work buffer, right? We could have printed like that. Right, so you just could have printed this thing directly. And if we put this in Flash, so we use the F operator, we need to change this declaration a little bit. You can look at the Arduino prog mem page for details about that. But if we change this definition and put these things in Flash, then all we'd need to do is print numbers at level, and we wouldn't need this 10 byte thing at all, or this 10 byte thing at all. So that would occupy 0. So now a call would drop from 16 bytes to just 6. So stuff like that. And then I had this other one, declaration of buffer command. Initially, I put this on the stack, but the way buffer command, initially I had it like this. Here, initially I declared the work recurs function like this. Now the problem with this is that it's going to allocate a character array of buffer size 80. Right, so there it is, in buffer size 80. So what that means is that if I have it set up like this, every time it recurs, it's going to allocate this 10 plus the 6 that it needs to keep track of other stuff, plus this 80. So now it's gone to 96. So 5 levels would be 500 bytes, and that's quite a lot. And it's not necessary because we only use it for this last one. So it'd be better to allocate it statically. So these are the sorts of things you need to think of. And just because it looks small, because it's just one line, it's not that much different to this, or indeed, this in I. It looks the same, but the impact is quite significant. So you kind of need to understand what libraries that you're calling do, and just bear in mind what they do occupy. And then can you think of any more? And as I said, there's lots of different ways you can do that, including compacting things. Don't use unsigned long if you only need an unsigned int, for example, or if your value is only going to be 1 or 2 values. Just compress them into a bitmap inside an integer or something like that. So again, there's lots of different things you can do. Now, the real problem we have here is, I've created a program that explicitly helps us diagnose this type of stuff, but it's not necessarily easy to sort of see where things go here. And as we saw when I ran that, I'll just recreate the example again. malloc 500A, 500B, malloc list. All right, so we've got our nice B structure there. If I run my test and then do the malloc list again, now it's corrupted. And if I go back to the stack dump, we can see that that's where we sort of last had visibility, but then all this other stuff happens as well, which has overwritten some of those Bs. It's not necessarily easy for you to find out at the lowest layer where that went to, because this is going to be somewhere in the internals of the Arduino library. Right, so it's not always easy to sort of see that. So you always want to try and make sure you have sufficient sort of overhead in memory to allow for this, which is one of the reasons why the compiler will give you a warning that says, warning if you use more than, I think, 90% or 80% of the BSS and data, it'll give you a warning that there's not much space left over for the stack. That's why it's giving you that warning, because it doesn't know how much is always going to be used, because that can be variable and random depending what's going on. And so it wants to sort of make sure there's some free space available for the stack. Okay, so while I was editing this, I decided I'd add a couple of modules to it. The first one I'm going to add is at the end of this video, and that covers looking at memory mapped I/O and how it can interact with the rest of the world. And then after I did that and I was editing some more, I was wondering how easy it was to detect this. And on the scale of how difficult it is to do things on the All About Arduino scale, turns out it's very solid, not too hard at all. So I just wanted to briefly show what I've done to support that. So I'll briefly go through the code here. I've decided I wasn't going to upload the code at all, but I will put it on Patreon. So if you want to instrument any of your applications with this, you certainly can do it. And I'll put detailed instructions on that rather than putting it in here. But we'll have a quick look at it anyway. Okay, so I have it already running. The first thing we'll note is that there's a few extra commands. So this dump and byte, that's what my future self will be looking at when I looked at the memory mapped I/O. And then I've added this status system here. And so I look at the code, we can already see a message that the monitor's reported. And that comes from this function here. So this print stack heap monitor status function produces that output. I won't go through that because that's not terribly exciting and not really part of the system, but you could certainly use that. But if I just enter the status command, then it'll produce that same output. And so what we have here is a counter So this is the number of times since the system has started that the monitor has checked the stack and the heap. And this is the lowest stack pointer found. So basically the furthest that this, where is it? The furthest that this orange arrow has gone downwards. I'll just bring up the monitor at the same time, I think. Yep. So lowest SP is the lowest the stack pointer has come down. So the furthest this arrow has traversed down towards the bottom of memory. And the BRK value is 0, meaning we haven't allocated anything on the heap yet. If I did, then we'll see that it's detected that there's been a change because the BRK value has now changed. So what we see now is the highest that the red arrow has gone upwards. So we can there's still quite a bit of a gap there. There's some, what's that? I shouldn't do mental arithmetic here. It's like C, 2C, so it's that almost 400 bytes of available space there still. Okay, so how does it work? Well, first of all, it's interrupt driven, and that's handled here by this attach interrupt. So if you did this by yourself, you could cause the monitor to be fired any way that you mean, any way you want to, but it needs to be interrupt driven. And why is that? Well, because when we looked at the corruption previously, we saw where our code in the recursion function went down to in the stack, but the corruption was much deeper. And so you need to be able to look at the stack pointer and the heap break value sort of independently of your program. You need to be able to try and get it to fire or look at the system when it's at the lowest possible memory. And so the easiest way to do that was via an interrupt service routine. Because what happens when you have an interrupt service routine, whatever's happening on the CPU gets interrupted, and then the return address of wherever it was when it was interrupted gets pushed onto the stack. So basically an interrupt service routine sees the current bottom of the stack. It always gets the lowest placement on the stack. So that's a good way of sort of seeing. And also it will fire independently of what's going on. It'll fire when it's inside the system functions or whatever. And so you can sort of see the most reliable chance of seeing the bottom of the stack. The drawback to that is that if it goes down quickly and comes back up, you might not see that peak. So that's just the trade-off. But using an ISR is sort of essential. And so that's the name of the function that we're going to run when we fire the interrupt. And that's just the variables that I use to track the various metrics, which I'll explain here. But here's the function that gets fired when the interrupt occurs. And so it increments the counter, which is this number here. So if I do it again, status, you can see that we've run some, 50,000 more times in that time that I've just been yammering on. And then what it does is it compares the current values, so in this case the break value, to the previously highest break value. And if it sees that the current value is higher than what we previously saw, it'll set this flag here to true to indicate that something has changed, and then it'll just record the current value. Then it does the same for the stack pointer, except in reverse. So if the current stack pointer is lower than the current low, so this orange arrow's gone further than we've seen before, set the fact that there's a notification available, and then sets the low stack pointer. And that does these ones as well. So if right now, when this ISR fires, if the stack pointer is below the break value, then that means we've had this collision occur, right? Because the orange arrow extends past the top of the red arrow, or reverse. And so, again, we record the notification, and then we count the number of times that we've seen this. And then even worse, if the stack pointer goes below the heap start, then we count that as well. So in that case, the stack pointer has gone all the way down here into the BSS and possibly the data and further. So we record that. And again, that's a counter, and those things are printed out here. So right now, we're seeing this check count, lowest SP and highest break value. So we're only seeing these lines at the moment because there's been no collision detected. Okay, but I'll recreate the test we did before and we'll see that. I won't create this because that's just be even more disastrous than any other form of collision. But I'll recreate this one using the previous test that we've just done. Now, how is this message here used? New stack heap notification? Good question. Basically, that's in our loop. So every time through the loop, I just check to see if there's a new stack heap notification, and if there is, then I'll print this message. Now I also do in buffer length equals 0. If you're just using the serial monitor, you don't need to worry about that, but the reason I've included that is because if I'm using putty and I've started typing in a message, I don't necessarily want that to sort of pop up in the halfway through my message. I've decided that I wanted to wait until the I've input the command and then I'll submit that message or print that message. And of course, we just register the fact here that it was false. Now, if you don't care about the notification coming out when it occurs, you can just remove that part. That's perfectly fine. I just didn't want to do it that way. Okay, so let's see if we can get it to do something else. Now, sometimes just running a command, you might get that to come up. It didn't here. It did when we first reset it. It came up twice. So what happened here was that the stack pointer went down to a certain level, and then within 5 ticks later, it went down a little bit further. So we got a second report here. Sometimes here's some more. So that's because I requested the status. When I did the malloc, that causes to go down a little bit further again. Oh no, that was because of the highest break value. Oh, but the stack pointer did go down slightly further, from 34 to 31. So you can see it's detecting these things independently of what we're doing here. Now if I run test 0, that's test. So I've currently got the recursion test with stack dump loaded. So if I do test 0, that should trigger a new message because the stack pointer will go quite low, and you can see it went all the way down to 677. And now we're sort of only 100 hex bytes away, so there's only 256 bytes sort of space available. If I run it again, it's possible that we might get another message if it sort of happens to see a lower value, which it doesn't look like it's going to. Now if I malloc some more, now what we'll have is a situation here where we've seen the stack pointer on this diagram sort of effectively goes somewhere down here into this collision zone. But that's okay because the break value is only sort of here. They still haven't quite met yet. But when I allocate this red arrow is going to pop up to here. Now, right now, the stack pointer is somewhere up here, so that's fine. There's not actually going to be a collision right now. But our most low stack pointer, let's say, is here somewhere, will now be below where the next 500 bytes will be. So we'll be malloc that'll go up to there. So I'll get a warning straight away for 2 reasons. One, because the malloc break value has changed, but also because the stack pointer extreme has intersected with the new break value. And so we can see here this warning risk of stack heap collision detected because this red line has now gone up past the lowest stack pointer line. And so there's potential for some overlap. Now if I free that, and then I run my test, that's all fine, that's all happy. If I print the status, we've still got that potential for the collision, but it wasn't actually a collision. So now if I malloc it again, I'll use C this time, just because it's fun, and run the test, then that will cause a collision. And so now we have this message, stack heap collision detected, as well as the risk. So this actually saw on 137 occasions, the stack pointer had descended down into the heap. And as we can see, we had that corruption there because that intersection occurred. So the lowest stack pointer saw was 677. Which is actually, wow. So it actually detected the bottom of the stack. So I'm impressed by that. So it actually detected that the stack pointer was here, which means it detected, in this case, the actual bottom of the stack. So that's, I don't know, pretty good in my mind. Now if I run it again, test 0, then we'll see that the number of collisions detected is now 273. So when I ran that again, there's another 273 times that observed the stack pointer and the break values intersected. Okay, so again, really all that's involved here is attaching this interrupt, and I'll look at the circuit that generates this interrupt. It's using an external interrupt on pin 2, I think it is, interrupt pin. Yeah, pin 2. And then it uses these variables here. So that the number of times it's checked, the current values for the extremities of the stack pointer and the break value, the notification, and then the 2 counters for whether it's been a stack heap collision or not. And then there's the actual check where all it does is counts the fact that a check has been done and then just compares the newer values. And then finally there's the print one, which just basically prints it all out. And of course you can print those variables however you like. So really all it is a function like this that checks it, the attach interrupt to set up the interrupt, and then this. Okay, so I said there was a circuit involved. So what I'm doing is I'm using a 555 timer. So this is an integrated circuit, an LM555, and you can find plenty of diagrams online about how to wire this up. And it's wired up in A stable mode. So that's not A space stable mode, it's astable, all one word, A-S-T-A-B-L-E, which means unstable. I don't know why they don't call it unstable. Astable is the word that they use. And what that means is it just constantly clicks over 10, 10, 10. And with this setup, with these 2 resistors and this capacitor, it generates a signal about every 570 or 570 times per second. And that's what I call the clock for the heap. And that goes into D2, which we already saw had the attach interrupt set up with it. So every time this one goes up, so I used rising. Yeah, there it is, rising. Every time the clock pulse turns from 0 to 1, that'll generate an interrupt, and then the heap monitor will check. If you did changing, I think it's changing, then you could get double the throughput, so it would be 1,140 times per second, or you could adjust these and have a different frequency as well. So, like I said, I'll put all of this up with more documentation on how to set it up in a upload onto Patreon if this is something you'd like to instrument your programs with. And as I said, I've chosen this because it's easy to set up. I can easily use the attach interrupt to link into it. You could use a timer interrupt. I chose not to do that. I've got other videos that show how to set up a timer interrupt, specifically one on interrupts. So if you want to use that, you can. But the main reason for doing that is that doing it this way is because, as I said, it is easy for you to set up. The coding is very simple. You don't need to muck around with CPU registers to set up a timer interrupt. And also there's less risk of a conflict. If you're using something that uses a timer, and I showed you a particular timer, then it'd be much harder for you to adapt. So using this method is sort of an easy way of doing it. And then when you're finished, you can just tie this to ground if you didn't even want to change your code, or just comment out the attach interrupt and it'll be effectively disabled. Okay, so hopefully that's helpful. That's a little monitor that sort of detects the risk of a collision here. And now that I've set that up, which I did specifically for this video, I think I might try it out in a few more of my programs and sort of see what's going on there, whether there's any potential issues. Okay, so that's it for the future editions. We'll move on to the next topic. All right, so I think we've done the stack and the heap fairly low level. Hopefully all that's clear. What I will do now is set up this test case, and I'll just upload that and explain what it's doing. Hopefully all of that's clear. It is a fairly sort of complex and mind-numbing subject, but it is important at least to understand the idea just when things start sort of going randomly off the rails to help understand what's going on there. Okay, so while it's uploading, it looks like it's done. So test list, yep. So this one has 4 test functions. I probably won't use the second one, but what they do is they allocate a string and initialize it with a value passed as the third parameter. So in this case, it would be like test 0 and then hello or something like that. Then test number 1 appends the supplied text to the string that was allocated in test 0. And I can pass multiple strings on that. So I can say test 1 hello there, for example. Read string is kind of a variation of 1, and that it reads something from the serial monitor. That would prove to be a bit tedious to use, so I won't bother. And then I've got this test 3, which simply prints out the string parameters. So if I run test 3, then it prints out stuff like that. So in the code, so here's test 3, print string parameters, just simply calls this dump string info thing. And I have this string object declared, test string, and it's initially set to string object. And then dump string info, so it produces all of this sort of stuff. Right, so what these things mean is string address. So this is the address of the string object. So that's the stuff that the string object uses to keep track of what it's managing, in particular this string. So it'll have things in it like how long it is, for example. The next one is the text address. So 472. So that's, can I have these both? Yeah. So that's a pointer to this. Specifically, it's a pointer to the letter S. And what we'll note here is from our segments that 410, i.e. this test string variable, is in this BSS section, right? So it is initialized, but it works slightly differently in that the initializer is code that lives inside this string object, right? So I don't think I have any here. Yeah, and I don't have any constructors in here, so I can't show you an example, but there would be code in this class definition that defines how that string is initialized. And that's why this goes in the BSS, because the compiler isn't necessarily initializing it. It's code in here that's setting the parameters. So that's why it's in the BSS. So 410, that's there. And then we can see the text address, which is where this letter S is. That's at address 472. And so where is that? That's in the, not no init, that's in the heap start. So that's in the heap. So indeed, if I printed that memory, 0x472, and it just happens to be 13 bytes long, which is what the next thing is, then we should see the word string object, and there it is. Right, so 472 points to the letter S, and then the subsequent addresses contain the rest of the letters. So I print that from 2 things. One is I use this CSTR function, so that gets the effectively a C string. It basically gets this pointer here, and then strlen can count the number of letters in a C string. So we get 13 out because, well, that's how many there are. I'm not going to count them. You can count them yourself. The second one is this s.length. So this is a function that the string object provides. So you can look at the string object in the Arduino documentation. So I think, is that in here? There, this one, string. So that's in the variables, and then string. So there's the C string function, and length. There's length. All right, so my string.length returns the length of the string in characters, and then C string converts the contents of a string to a C style string, which is why it can work with strlen. So that's why both of these say 13. And then lastly, size of. So I did look at that before, where I was looking at the size of, I think it was an array of some kind, and it gave, the work buffer, and it gave me 10, which was the number of bytes in it. So this size of is printing the size of this, the string that's passed to it, which is this test string. So this is 6 bytes, and this will always be 6 bytes. So this part will become 6 bytes all of the time. And then lastly, I'm printing the string. Okay, so let's look at a few more aspects of it. 128. So I just set that up first. And so I already did the dump of this 0x472, but what about this one? And just take it on faith that it's 6 bytes, because that's the size of the string for now. And so we look at it and we get that stuff. Now I can sort of see some things that make sense already. So we've got this 13 bytes. So 13 in hex is a D. Clear. Right, so it's 13, so that's a D. So either or both of these is the string length, I guess. And then we've got this 472. Remember, we reverse them because that's the way the little endianness works. And 472 just happens to be this. So this is clearly the pointer to where the actual contents of the string is. So the contents of the string isn't actually in the string object. It's on the heap, which we already identified here. And if I dumped the heap, just more generally, we can see string object, and we can see that there's got this 000E. And so why is this E, but that's D? That's because C strings require a null terminator. So the size of the malloc space will always be one more than the length of the string. So if it's got 13 characters, there's the 13 characters, and there's a null terminator. And note that we've still got the A's left over from before. So this heap is just effectively random. Those from the mallocs, the 500 of the A's and the B's and whatnot from when I was looking at the collision. So let's see if we can adjust this, and I'll just run these again. So I'm going to use test 0. So I'm going to allocate the string and initialize it with the parameter 3. So test 0 is set string to token. That's this one. Again, refer to the command and control if you want to understand how this works. But I have added an extra parameter to the control function, which is describe. And that's what the test list basically calls this all of these functions with the describe parameter, and then it returns. So effectively, when I do a test, it calls it twice, once to describe it, and then once not to describe it to actually run it. But anyway, what it does is it takes the third token. So that's why it's test 0, for example, hello. And then it basically sets the string to the third parameter. Because remember, these start at 0. And then it'll dump the string. All right, so test 1, and I think, test 0, and I think we'll use high. and then dump. What should we look at first? I think we'll look at the string. Yep. And so there we have our pointer, so 472, so that's still the same. And we've got 2 bytes in it. So this value, which was 0D, as we can see there, is now a 2, and this 0D hasn't changed. Okay, so interesting. Let's do dump heap. And now we can see that we've got the string high, and then we've got this dot here. So that corresponds to the null. So now we've null terminated the string, and then we've got this leftover stuff from our initial allocation, and then there's all this other leftover stuff from our previous round of tests. And we can still see that this segment is 0e, which is one more than the size, one more than the initial size of the string. So D. So what's this D? The only way we can sort of understand that is if we look at the source code. So this is the source code for the string object. It's in a file called wstring.h, and you can see the path there if you're interested. Obviously that's a Windows path. You would need to locate the equivalent if you're using Mac or Linux, but it'll be something along those lines once you get into the Arduino IDE. And there's a whole bunch of stuff here. So there's references a flash string helper. We'll see those more in the print methods. Oh no, that's actually from somewhere else, so forget that comment. But then we get down to this protected bit, and we can see here that there's 3 variables that are declared. So one is a pointer to the buffer, which looks somewhat suspiciously like that. Then we've got this capacity thing, which is somewhat suspiciously like that. And then we've got this len. So that's that one. All right. So this D is the capacity. And so you can look at the code yourself if you want to. It's fairly lengthy at 750 lines, and it does call other stuff. But essentially what it's doing is it's using this capacity to know how much is allocated on the heap. And so if we try and append more data to it that exceeds this capacity, then it'll do something about resizing what memory it's got on the heap. So they're the 3 variables: pointer, current capacity, and current length. And so we can only see this. It doesn't, unfortunately, the string object doesn't provide a method where we can extract this, so you can't see what the current capacity is. But there is a function reserve, which does talk about this. So the string reserve function allows you to allocate a buffer in memory for manipulating strings. So my understanding is you can call that at any time, and that'll just set it to the whatever value you want it to be. I won't bother with that. You can explore that by yourself. I also won't bother with this anymore. And so we'll come back to here. And what I'm going to do is I'm going to use the next test, append token 2. So right now we're in a situation where we've got 2 bytes allocated, and we've got 0D, which is I think 14 bytes available to it, 13 bytes available to it. And I'll append this string to it. Now this string is 2, 4, 5 bytes, it will also append a space. So we should end up with high space there. So that'll append the 5 bytes of there plus this 1 byte of a space. So 6 bytes to it of the 2 that's already there. So it should grow to 8 bytes. That means it should still fit into the 13 we've got available. So all it should do is just overwrite some more of this original message here. So let's just do that and see what happens. So our pointer is still 472, so that's good. It now says it's 8 bytes. The size of the string is, so the string object is still 6 bytes because that's just those 3 values that I looked at just now. But the length is now 8. So if I dump the heap, then we can see there's our message hi space there, and there's a little bit of the string object message left over from before. So we still have a little bit of space. It's currently using 8 bytes. It's dump that one. So you can see there's our 8. It's still got 0D left, 13. So there's still a little bit of space there. So let's try doing this again. And this time I'll make it a bit longer. So this is now, what's that? 2, 4, 6, 7, 8, 9, 10. So 8 plus 10 is definitely going to exceed this capacity. There's the capacity 0D. So let's see what happens. So we're still at 410. The pointer is now still 472, so that's the same as before, but now it's 19 bytes. So if I dump that, we can see that both of these have grown, so the capacity is now the same as the size. And dump heap, that'll be good enough. And we can see, hi there, what's up. It's expanded that, and now this size in the malloc block is 14. Which, remember, we need to have one more than the size of the string because we need to allow for this trailing null that terminates the string. Okay, so that's great. And if you're only ever going to do that with one string, then this is perfectly fine. There's no problem. But what if you're not going to only do this with only the one string? Or worse, what if you're going to call functions that do dynamic memory allocation? Like, for example, a JSON parser is likely to do some dynamic memory allocation. Or you're going to create multiple strings, substrings and things like that. So I haven't set this program up to do this, but I do have the malloc, and that effectively does the same thing. So since the string uses the heap, it's internally using a malloc. We might even be able to see that. No, I'm not sure where it's doing the malloc. I just quickly searched the source code and I couldn't find it, but it's using malloc to do this. In fact, what it's doing is it's using realloc. So realloc is like malloc, except it can change the space. Here we go. So it's doing realloc. So that's what we saw happen just now. It realloced the string and increased the amount of space. And that internally has the same sort of operations as malloc if it needs to move the buffer, and we'll see that shortly. And then there's other functions in here that will actually copy the data over. In fact, there's a copy there. So anyway, I'm not going to debug the string object. We'll just look at how it behaves. And so my point is that if we allocate more of these things in memory, then we can start to get a fragmentation problem. So what I'm going to do is do that now. So first of all, I'll just demonstrate that we've got nothing on the free list. So basically the free list starts here at 486. So immediately after the null terminator from our current string. Okay. So malloc 10 bytes and fill it with an A. If I dump the heap, then we can, maybe I should have used a different letter, but anyway, we've got that 0A, 00, and then we've got the bytes. I should have used a different letter, sorry about that. But you'll see the effect later on, because it's definitely only 10 bytes, because now we've got this 10 here now, so something has changed. It's used up these two and replaced it with a 10, so that means we've got the 10 A's there. So I'll now append a new message to our string. And the key thing to note here is, before I do that, I'll just do test. I think it was 3. Yep. The pointer is 472. Test 1. Howdy. So we can see already that the pointer has now moved. The string object is still at 410 in the BSS, but now our pointer has moved and we've got 26 bytes. So if I dump the heap, we can see that there what's up is still there, but now we've got another copy, hi there what's up and howdy, and that starts at 494. So there's 490, that's 490, 491, 2, 3, and 4. So it starts here. And then if we look at this one back here, we can see that now we've got this, the high that was originally here has been overwritten with a 0, and we've got this 1400. So what that means, it's the string courtesy of that realloc. The realloc has released this because it can't fit it in here and given the string a new pointer for the actual data. So if we look at the free list, we now have one object on the free list, and that starts at 470, and it's 20 bytes, because remember this is hex, so 10 in hex is 16 decimal plus 4, so that's 20, and then there's no next pointer. So the key thing here is the buffer is moved, and there's now one segment on the free list. Let's set up another barrier. This time I'll use B. And so we can see it's put that here at the beginning. And the reason for doing that is because I requested 10, but there was 20 available, so it could squeeze in there. And if we look at our free list, we still have one entry on there, and there's 8 bytes. So let's set up another one. Now our free list still shows the 8 bytes because this 10 obviously can't fit into the 8, so it had to allocate more memory. And if we dump the heap, we should be able to see the C's starting immediately after our string content. So hi there, what's up, howdy, full stop, and then the null. Then we've got this 0A followed by this 00, which is the length of this block, and then we've got these 43s, which are the C malloc block that we have. So now, if I append more data to it, what do you think will happen? Can you guess? Hopefully you guessed that the pointer will change. So now it's pointed 4BD, which is what, 4B and then D. So that's this byte here. And the reason it's doing that is it needs the size value here, and then we'll have our test string. So if I dump the heap, so it's starting to get a bit jumbled up, but we've got our A, which is the first one we allocated, then we've got our B, which is the next 10 we allocated, then we extended our string, then we've got the C, and then we appended more data to it, which is this here. But there's not enough room here because this C is now blocking it, so now it's moved it over to here. So if I do free list, we should now have 2 objects. So we've got this 8, which is starting to get a little bit unusable. We've got this next one at 27, which is essentially this block here to howdy. That's the 27. It starts here. That's the size 1B. That's 16 plus 11, so 27, and then nothing after that. So we've got this, and we kept going. We would eventually run into problems. So now that we've got these 2 free blocks, a total of 35 bytes. And they're sort of starting to get unusable, and you can sort of see that the stack is creeping up bigger and bigger and bigger and getting close. Sorry, the heap is creeping up and getting further and further to higher memory addresses, which means it's getting closer and closer to the stack, which means getting closer and closer to this if we don't manage it. And as we use more of these things, the chances of gaps appearing and not being able to be reused and the fragmentation can increase, and so that can increase the problem. So like I said earlier, if you're just using the one string and you're just reassigning it and resetting it all of the time, then that's fine. The heap is just going to grow up and down and not continue to expand. Just like the stack will grow up and down and won't continue to expand. But unlike the stack, which is quite orderly in that you have to pop off the values you push on, otherwise things will break immediately, the heap can be a little bit more haphazard and Wild West because you can get these little holes here which just effectively are not usable. And of course, if you have a bug in your program and you lose track of one of the segments you've allocated, then that's just permanently like a rock. It's just stuck there. And so then just a final look at our string object. 6 bytes long. We can see here that, oh, that's the wrong one, wasn't it? 10. Stringer S410, yep. We can see near here now that the pointer is 4BD, so check. Its size is 25, so remember that's hex, that's 2 times 16, 32, plus 5 is 37, and if I run test, was it 4 or 3? 3, I think. I get 37, so 2 16s is 32 plus 5, and the capacity is 25, so if we appended more stuff to it, then it would be reset. Now if I reset it to hello, then not much will change. The pointer, it'll still be using the same buffer. There's no point moving memory around or allocating a new block, but what we will have is plenty of free space, because right now we're only using the 5 bytes for this hello, but there's 25 hex available, and so since it's not needed to allocate or do anything special with that, it's just continuing to use the block that it has. Right, so as you saw before, there's the hello with the null terminator. That's this byte here, that's that dot, and then whatever was there before is just sort of left sitting there, waiting to be overwritten by any other requests. Okay, so I'll just finish up looking back at this diagram, and I want to focus in on this memory mapped I/O. I wasn't really going to cover it because it's not really about how the CPU or the compiler manages memory and those sorts of issues, but there is this mysterious 100 hexadecimal bytes down here, which I've sort of fobbed off as the memory mapped I/O. And that's used for I/O registers. And what happens is the MCU maps certain functionality to RAM locations that we can just read using normal memory access. And since we've got a test program that can do that, I thought, why not just have a look at some of this? So examples of things that appear in this memory mapped I/O is the serial ports, so the USART port hardware, and you interact with that by reading and writing data to this memory mapped I/O. Timers, I2C, the GPIO pins, which is what I'll be looking at here, and more of the CPU's capability, so analog digital conversion, stuff like that. They're all accessible through ports in here. And the reason I focus on the GPIO is because it's fairly simple and fairly direct, and we can actually see how I can do stuff in the real world, and that affects the registers, and also do stuff to the registers to affect the real world. And so what I'm going to do is I'm going to use some switches, which I'll connect to GPIO pins 8 to 11 on the Arduino, and a couple of LEDs connected to pins 12 and 13 on the Arduino. So that's those pins over here, but we don't reference them as pins 8 through 12, or indeed whatever they connect to on the actual chip here, which is actually not 8 through 12, it would be something else, but through the register. And so what does that look like? Well, I'm going to set up a circuit like this. So I'm going to have 4 little switches that connect to pins 8 through 11, as I said, and the 2 LEDs. But we access that through a register called port B. And port B is a structure that consists of 3 registers. So there's the actual register called port B, which is the output register. There's DDRB, which is the data direction register. And there's pin B, which is the input register. And those descriptions are kind of generally what they do, but there's a little bit more to them, and they do have sort of, let's say, extra capabilities depending upon what mode they're in. And these numbers here, 23, 4 and 5, are the addresses in memory. So that's the address of port B in this memory mapped I/O here. And where does that come from? Well, that comes from the ATmega 328p datasheet. And also this mapping comes from this pinout diagram. So what we can see here is this yellow column here. And unfortunately on this diagram, I guess the legend says that that's control. Okay, that's the controlling for this. But the key thing here is the label. So PB0, PB1, PB2, and so on. So that means port B, and then bit 0, bit 1, bit 2, bit 3, bit 4, bit 5. So what I should be able to do is flick the switch, and I should see the low order 4 bits change depending on the switch settings. And I should be able to write data to it and set bits 4 or 5 and affect these LEDs. Now, note that this mapping of GPIO pins 8 to 11 and 12 to 13 to port B is unique to the Arduino Uno. Okay, it's unique to this model. If I look at a different one, for example, a Mega, then the mappings are going to be different. So, GPIO pin 8 on the header would actually be port H, bit 5, so H5. Next one, 9, that would be H6. 10 would be port B, bit 4, as opposed to bit 2. And the next one would be port B, bit 5, and so on. So they all vary depending upon the actual hardware. And in part, that's to do with what the functions, the extra functions of the pins are. So for example, here we look at pin 5. That has a PWM capability. So when Arduino designed these, they tried to give some sort of compatibility and sort of always ensure that pin 5 on a Mega would be PWM. But on the MCU, I guess the hardware associated with this particular PWM, which has some other functions as well, would be provided on a different port on the Mega. And so the CPU pins or the MCU port mapping is a little bit different on each model because of the different architecture of those MCUs. So this is the actual schematic that I have. So in this yellow bit here, that's the GPIO pin labels. So I've got pin 8 goes to this, if you like, the rightmost switch on this little switch block that I've got. Then the next one goes to the next rightmost pin, so the second one, third one, fourth one, and then I've got 2 LEDs connected to pins 12 and 13. Alright, so I think I'll leave that diagram there. And I've got this test program. It's got a couple of tests in it. One which, well, I'll just run it. Alright, so we won't need that anymore. If I just run this test list. Alright, so we've got these 2 tests here. I've got one where I can write data to memory, and I've also got the print port B values. I do have added some other commands to this, specifically dump byte, which if I want to focus in on something I can use, but I probably won't bother with that because I have this test 1, and we'll use test 0 to write to it. Okay, so let's try setting some things. So right now, all of these 4 switches, and it's these 4 that are relevant as per the circuit diagram. The on position is this side, so these 4 are on, and because I have pull-up resistors, that means that when the circuit is closed, it's connected to ground. So each one of these should read as 0. And sure enough, if I look at the test 1, I'll just bring that again, they're all 0. But if I switch one of these down, so that breaks the connection to ground, which means now this is pulled high, so it should read as a 1. And sure enough, it reads as a 1. If I pull this one up and pull this one down, now this second bit here will be high, so that's this one here numbered 7, and that connects to D9. Actually, maybe I'll go back one. I think that's a better representation because we can see that bit 9 is port B number 1 bit. And so now we see it's 2, right? Because you have to think about the binary arithmetic. This is bit 0, so that's 1. This is bit 1, so that's 2. And if I use the dump byte command, there was a good reason for using it. So we're wanting to read the input register. That'll actually display it in binary as well, so we can see that here. So the output here is the hexadecimal value, the binary equivalent of that, and that's the decimal value. Now if we do the same thing, continue along, that one on. So now we have 1, 2, 4, so now it should read 4. I think I'll use that one, dump byte. So we can see it's 4. Let's keep going. This will show 8. And of course I can do combinations. So 8 plus, that would be 8 plus 1 would be 9. And we should see those 2 bits set. So what you can see here directly happening is that as I adjust this external hardware and change the electrical settings here from 0 volts to 5 volts, depending on where the switch is open or closed, we get a 1 or a 0. So down is 1, up is 0. Okay. If I did test 1 again, we can see that that's also got the 9. All right, so how are these other ones used? Well, so DDRB, that's the data direction register. So if the value is 0, which is the default on power up, then it's configured as out. The corresponding bit is configured as input. If I set it to a 1, then the corresponding bit is set to an output. So 1 is output, 0 is input. So right now, DDRB is 0, which we can see there. Now, because these are connected to bits 4 and 5, that'll be the second half of this hexadecimal value. So this digit, or the low nibble, these half 4-bit groups are called nibbles. This low nibble is 8, and so then the first bit on the port in the second nibble with bit 4 is 1, so that'll be, if you like, 10, and this one's 20, so 13. So what I'll do is set it to 0, set those 2 bits to output. So test 0, DDRB, 30, like that. Now, I should actually set this back to 0 so it doesn't have some undesirable influences. As I said, there's certain different modes of operation depending upon what the settings are. So I'll set that to 0 and then write that to DDRB. Basically, if we're writing bits to, I can't remember which way around it is, and then set the DDRB register, that would enable the inbuilt pull-up resistor, and I didn't really want that to happen. Anyway, we can see DDRB is now 30. So 24, yep. So we can see that that's those 2 bits that correspond to PB4 and 5, because if I count from here, this is PB0, PB1, PB2, PB3, PB4, PB5. So that means that these 2 bits are output, and that's appropriate because that's where our LEDs are connected. So now I can write to port B, test 0, 5. And if I write 10, then that should set this corresponding value to a 1. And so we should see one of the LEDs come on. And sure enough, hopefully you can see that, this one is turned on. If we set it to 20, then the first one will turn off and the next one is on. So, yep, check. If I look at that, we can see that we've got the 20 there and the 30, and that is being reflected over here in the input. Now I can actually still use these. Set that one down. All right, so we can see that the input is still reflected while the output is still there. I'll write a 1 to this to make sure I don't have any adverse effects from now on. So 1. And if I set this to 30, then you should see both LEDs turned on. Okay. Now, as I said, these things have different modes. So pin B is the input register, and it has a different effect if I write to that one. So test 0, 0x23. And so if I write, let's say 11, then I'm writing 11 because I want to keep this bit as its input, and I'm going to write a 1 to effectively this bit, and then write a 0 to this bit. That's the change. That's the significance. And so what will happen is when I do that, if I write to pin B when it's in output mode, then this is just how I remember it, but the in becomes invert, not input. So let's try that, and what we should see is that the LED, one of the LEDs will turn off. And sure enough, that one's turned off. Now if I do it again, it'll invert it again, and so now it turns on again. And I can keep doing that. I don't want to do 31, do 11. So every time I do that, that LED will invert. And I can do the same for the other one. 21, it'll invert. And if I did make that 31, then they'll switch, because both of them are being inverted. Okay. Now we can also use these things in our programs. So Microchip, they provide a header file which the compiler includes. Well, it doesn't really matter that much, but many of these symbols are defined. So here is a blink program that uses the low-level hardware. If I upload that, I won't bother saving it, then what we should see is port B5 blink. So that's one of those LEDs. So while it's uploading, just briefly explain what it's doing. It's setting DDRB so that bit 5 is a 1, which means that it's setting bit 5 to be an output. And then in the loop, apart from this delay, which is obviously an Arduino function, it's just writing a 1 to bit 5 in port B. So pretty much what I was doing up here in this test program. And as you can see, well, it prints the invert message, so we can see that scrolling off the screen. I'll put the timestamp on so we can actually see something happening. So it's printing the invert message. It's writing that 1 to port B5, and there's an LED connected there, so we should be able to see that this one is blinking as a result of that. So this is what's referred to as bare metal programming, or low-level programming. We're actually directly manipulating the CPU registers. And so the last thing is, how do we know where that information comes from? Well, it's from this data sheet. So I'll put that there, and I'll put this program here so we can see that. There's that, we don't need that. And so this PDF is the what's called the data sheet for the MCU, and this one in particular covers this range because they're sort of similar, they're just different in memory sizes, but it covers the ATmega 328P, which is the MCU that's on the Arduino Uno. And it's some 662 pages, so it's not light reading, it's actually more of a reference manual. There is a chapter here called I/O ports. Now if we click down to there, then this explains how the I/O ports work in this particular MCU, or this particular family of MCUs. And then there's a section down here, register description, and that basically shows you the details about each one. And importantly, or of interest, it does give you the address. So this this number in brackets here, 25, 24 and 23 is the addresses that we were using earlier. And I'm going to say often, maybe always, but certainly very often, this is the name of the register that you can actually reference directly in your C program. So that's why this program compiles and works, because there's a header file that comes with the compiler that when you select Arduino Uno in this menu setting, it uses the header file for the Arduino Uno, and that will have entries in it that says that port B5 is at address 25, and that's how this works. And also how it works on a different MCU like a Mega, which also has a port B, but the address would be different. I won't look that up, you can find that by yourself. Okay, and then above it will say things about how we can use these different registers. So for example, so here's what it was talking about. I was talking about switch between input and output. You sort of need to be a little bit careful about how the other registers are set, because it's sort of a bit of a complex process. Well, not that complex, but a detailed process you need to be aware of when you're changing states. Okay, so as I said, these aren't terribly easy to read. If you do read through the 662 odd pages, or focus on this section more precisely, you will find things, little gems hidden away in there somewhere. Here we go, like this one. So there's just this one almost throwaway line that says, writing a logic 1 to a bit in the pin X register will result in a toggle in the corresponding bit in the data register. And the data register was port B. And it's that one sentence that basically allows this program to work. Because when we write a 1 to a bit in the pin X, so X is B, C, D, whatever registers the MCU has, writing a 1 to a relevant bit in this pin X register will cause a toggle in the corresponding bit in the actual data register, which is the output register. And that's why this LED is blinking. Okay, so how does that relate to the Arduino functions, such as digital write, pin mode, and things like that? Well, basically, when you specify a pin, so for example, pin 8, there's a lookup table in memory that it uses to work out that for an Uno, that would be port B, bit 0. And then it adjusts those bits just like we did in this test program. Similarly, for the Mega, there'll be a different lookup table that says port 8 or pin 8 relates to port H and bit 5, and it'll do the appropriate things depending upon what the function is that you requested, like pin mode or digital read or digital write and so on. So hopefully that was interesting, gives you a bit of an insight into how the I/O works on the MCU. They're not all the same, but generally there's a memory map I/O capability, and you can just use regular random access memory instructions to read the values from these connections into your code, which is running on this chip. So hopefully that was informative. As I said, I think I'll leave it there for now. What we looked at here was how memory is used, the different memory types. I drilled in specifically onto the AVR MCU, specifically the ATmega 328P, which is found in the Uno R3. But the generic concepts are applicable to other MCU architectures, particularly some of the constraints about the heap and the flash. It's just that sometimes other CPUs have much bigger addresses or much more available memory, so the risk is a bit less. In terms of the collision is a main issue, but the general concepts would apply anyway. So, yep, I'll leave it there. So once again, thanks for watching. Hopefully you got something out of this video. If you did, then please like the video. Leave a comment what you thought, any questions you have. If they're complex questions, maybe post them on Reddit. You can always ping me over there. I'll leave the profile in the comments. Don't forget to subscribe so you can see future videos when I release them. Check out some of my other videos. I mentioned the serial command and control A lot of this video has been built upon the things that I show in there. Subscribe to my channel and turn on the notifications, and hopefully we'll see you next time. Thanks for watching.
Alright, so thanks for watching. Hopefully you found that of interest and useful. You may well encounter some of the things I talked about as your Arduino career progresses. If so, hopefully those things I showed you can help explain or help you understand what's going on when things don't go well. So yeah, with that, I think I'll end it there. Please leave some comments. Especially find it interesting to see what you thought about the content and whether there's any questions. But also like this video if you got something out of it. Subscribe to my channel so you see new videos when I post them. And look for me on social media. I mentioned Reddit, also Buy Me a Coffee and Patreon and other sources such as LinkedIn. Okay, so thanks for watching. Bye for now, and see you next time on All About Arduino.